Look out at the night sky. What do you see? A vast ocean of stars, distant galaxies, shimmering lights against the infinite black. But what if I told you that everything your eyes can perceive, all the glittering points of light, the swirling cosmic clouds, the planets and the suns, what if all of that made up less than 5% of the universe? The rest is darkness, an invisible, mysterious presence that holds the cosmos together, yet slips through our fingers every time we try to grasp it. We call this era of discovery the cosmic dark matter era, and it's one of the most profound and puzzling chapters in the story of our universe. For decades, scientists have known something was missing. Galaxies spin faster than they should. Light bends in ways that can't be explained by visible matter alone. There is a ghost in the machine of the cosmos, an unseen force sculpting the universe on a scale so grand it defies imagination. This isn't science fiction. This is the frontier of real astrophysics, where the rules we thought we understood begin to blur, and the deepest questions about existence itself come sharply into focus. What is dark matter? How does it shape reality? And why, after all this time, does it remain so utterly elusive? In this video, we're setting out on a journey into the heart of this mystery. We'll explore 25 of the most mind-bending puzzles that define the cosmic dark matter era, each one challenging not just what we know about the universe, but how we know it. From the way galaxies cluster in silent, invisible webs to the strange particles that might be flowing through you at this very moment, we're diving into the unknown. This is more than a list of facts. It's an invitation to wonder, to question, and to see the cosmos in a completely new light. So settle in, open your mind, and let's begin. Our story begins not with a flash of light or a dramatic explosion, but with a quiet, persistent anomaly. A puzzle first noticed by a brilliant and often overlooked astronomer working in the 1930s. His name was Fritz Zwicky, and he was studying a massive group of galaxies known as the Coma Cluster. By carefully measuring the motions of these galaxies as they swung around their common center of gravity, Zwicky made a startling calculation. The individual galaxies were moving at such tremendous speeds that the gravity generated by all the stars, gas, and dust he could see simply wasn't enough to hold the cluster together. According to the known laws of physics, the Coma Cluster should have flown apart eons ago. Yet there it was, stable and intact. Zwicky proposed there must be some form of Dunkel Materie dark matter, invisible mass providing the extra gravitational glue. At the time, his idea was so radical that many in the scientific community dismissed it entirely. The mystery would lie dormant for decades until the 1970s, when an astronomer named Vera Rubin provided the undeniable proof. While studying the rotation of individual spiral galaxies, Rubin and her colleague Kent Ford expected to find something familiar. Think of our solar system. The inner planets close to the sun's immense gravity orbit very quickly. The outer planets, like Neptune and Pluto, move much more slowly in their distant, stately paths. Rubin assumed the same principle would apply to galaxy stars close to the bright center should orbit quickly, while stars out in the dim edges should be sluggish. But her observations revealed something astonishing. Stars at the very outskirts of galaxies were whizzing around just as fast as those near the center. It was as if the entire galaxy, from core to halo, was a single, solid disk spinning in unison. The only possible explanation was that each galaxy was embedded within a gigantic, massive sphere of something invisible. A halo of dark matter whose gravity was tugging on those outer stars, accelerating them to impossible speeds. This gravitational evidence is now overwhelming. We can map the distribution of dark matter by watching how its immense gravity bends the light from even more distant galaxies, an effect called gravitational lensing. These cosmic maps reveal a hidden architecture to the universe, a vast, invisible scaffolding upon which the visible galaxies are merely hung like dewdrops on a spider's web. The scale of this discovery is almost incomprehensible. For every ounce of atoms that make up you, me, our planet, and every star we can see, there is at least 5 times more dark matter out there unseen. It is the dominant form of matter in the cosmos, the primary ingredient in the cosmic recipe, and this is what makes it mystery number 1. This isn't a small accounting error, it's a fundamental crisis in our understanding of physics. The Standard Model, which brilliantly describes all the known particles and forces, has no place for a particle that fits this description. Whatever dark matter is, it does not interact with light or electromagnetism at all. It doesn't absorb light, reflect it, or emit it. It only seems to interact through gravity and possibly the weak nuclear force, making it nearly impossible to detect directly. We are surrounded by it, bathed in it, every second of every day, with trillions of these particles streaming through our bodies without a trace, and we have no idea what it is. The missing mass problem forces us to admit that most of the universe is made of something we cannot see, cannot touch, and do not understand. It is the ghost in the cosmic machine, and its discovery was the first crack in our settled view of the heavens. So we know the dark matter is there, its gravitational pull undeniable. But this realization only leads us to the next, even more profound question: what exactly is it made of? We've given this cosmic ghost a name, but we have yet to see its face. This brings us directly to mystery number 2, the fundamental nature of the dark matter particle itself. For decades, the leading theoretical candidate has been a class of particles known as WIMP, or weakly interacting massive particles. The hypothesis was elegant and compelling. These particles would be heavy, perhaps dozens or even hundreds of times the mass of a proton. Crucially, they would not interact via the electromagnetic force, making them invisible, but they would feel the weak nuclear force and, of course, gravity. This theoretical framework was beautifully supported by a concept from particle physics known as supersymmetry. Supersymmetry proposes that every known particle in the Standard Model has a heavier, as yet undissected, superpartner. The lightest of these superpartners, theorists suggested, would be stable, neutral, and pervasive, a perfect WIMP candidate for dark matter. Even more enticingly, calculations showed that the thermal relic abundance of such particles left over from the Big Bang would naturally account for the exact amount of dark matter we observe in the universe today. It was a perfect golden hypothesis. This elegance fueled a monumental global effort to find them. Deep underground, in mines and beneath mountains, scientists built exquisite experiments to shield them from the constant rain of cosmic rays. Detectors like LUX, xenon, and Panda X were filled with ultra-pure liquid xenon, waiting for the incredibly rare ping, the minuscule flash of light or charge that would signal a WIMP bumping into the nucleus of a xenon atom. These experiments are marvels of engineering, so sensitive they could hear the proverbial pin drop in a cosmic hurricane. Year after year, they grew larger and more sensitive. And year after year, they found nothing. The parameter space where WIMP were predicted to live has been systematically carved away, leaving the once golden hypothesis on increasingly shaky ground. The silence from these detectors is in its own way one of the loudest results in modern science, forcing a profound and necessary re-evaluation. This null result has energized the search for alternative candidates. Perhaps dark matter is not heavy but incredibly light. The action is one such candidate, a hypothetical particle born out of a solution to a different problem in particle physics. Billions of times lighter than an electron, actions would behave less like discrete particles and more like a pervasive, oscillating energy field flowing through the cosmos. Their detection requires a different kind of ingenuity, using powerful magnetic fields to try and convert them into faint microwave photons. Then there are sterile neutrinos, hypothetical heavier cousins to the known neutrinos that could decay and produce faint, telltale X-ray signals that astronomers are now scouring the sky to find. There are even proposals that dark matter could be made of primordial black holes, tiny black holes forged in the seething chaos of the very first moments after the Big Bang. Each candidate opens a new window into potential new physics and presents a unique set of daunting experimental challenges. The pursuit has expanded from deep underground labs to particle accelerators trying to create dark matter, to telescopes in space and on the ground searching for its indirect signatures. Identifying this particle is not merely an academic exercise, it represents the most urgent question in particle astrophysics. Until we know what dark matter is, a staggering 85% of the matter in the universe remains a blank page in our textbook of physics. We are surrounded by an ocean of something fundamental, and we are only just beginning to learn how to see. But if this missing particle is the ghost in the cosmic machine, then its gravitational effect should be perfectly predictable, right? We should be able to model exactly how this invisible matter clumps and structures itself throughout the universe. Yet, when we compare our most sophisticated theoretical predictions against the cold, hard data from our telescopes, we find another glaring contradiction. This is mystery number 3, the core cusp problem, a puzzle that reveals a surprising delicacy in the dark side of the cosmos. Our understanding of how dark matter should behave comes from incredibly powerful computer simulations. Scientists run what are called n-body simulations, where they model the universe as a vast collection of particles, millions or even billions of them, representing dark matter. They set the rules based on our standard model of cosmology and let gravity do its work over billions of years of virtual time. These simulations are breathtakingly successful on large scales, producing the vast cosmic web of filaments and voids that we observe in the real universe. And they make a very specific prediction about the distribution of dark matter within individual galaxies, especially small, faint dwarf galaxies that are believed to be dominated by dark matter. The simulations consistently show that dark matter should form a cusp in the center of these galaxies, a sharp, steeply rising peak in density right at the very core. It's a natural outcome of how gravity pulls this invisible material inward. But when astronomers turn their telescopes to actual dwarf galaxies and measure the motions of their stars to map the underlying gravitational field, they find something completely different. Instead of a sharp, dense cusp, the data suggests a much gentler distribution, a core of roughly constant density. It's the difference between a towering, pointed mountain peak and a flattened, rolling hill. The stars in these galaxies are moving in a way that indicates the dark matter is more evenly spread out than the simulations said it should be. This isn't just a one-off anomaly. It's a persistent discrepancy that shows up again and again in our observations of these small, dark matter-rich galaxies. So, who is wrong, the incredibly accurate simulations or our meticulous astronomical observations? This core cusp problem forces astronomers into a fascinating detective story with two primary suspects. The first possibility is that our simulations are incomplete because they overlooked a key ingredient, the messy, violent behavior of normal matter. Those early simulations focused purely on dark matter, treating the stars and gas as passive bystanders. But we know that normal matter can fight back against gravity with tremendous force. When the first generations of massive stars in a dwarf galaxy are born, they live fast and die young, exploding as supernova. These colossal explosions blast energy and gas outward, essentially punching the dark matter in the gravitational gut. This process, called feedback, could physically push the dark matter around, smoothing out the dense central cusp into a more distributed core over billions of years. Similarly, the intense energy output from a supermassive black hole, an active galactic nucleus at the heart of a galaxy, could act like a cosmic bellows, stirring up the dark matter and preventing it from settling into a steep cusp. The other, more radical possibility is that our fundamental understanding of dark matter itself is flawed. Perhaps dark matter isn't completely cold and collisionless as the standard model assumes. Maybe dark matter particles can interact with each other through some unknown force stronger than gravity, causing them to bounce off one another and avoid becoming too densely packed in the center. Or perhaps dark matter has a small intrinsic velocity that prevents it from collapsing into such a sharp peak. These ideas would require a significant shift in our particle physics models, moving away from the simplest assumptions. The core cusp problem is more than a technical disagreement between theorists and observers. It's a profound reminder that the universe is a complex system where everything is connected. It suggests that the story of galaxy formation isn't just about dark matter providing the scaffolding and normal matter simply falling into place. Instead, it might be a continuous and dynamic dance, a feedback loop where the ordinary matter we can see actively shapes and is shaped by the invisible dark matter we cannot. Solving this mystery means learning the steps to that dance, revealing a universe far more interactive and surprising than we ever imagined. While the core cusp problem presents a fascinating puzzle within individual galaxies, an even grander contradiction emerges when we zoom out to look at the entire galactic neighborhood. Our most powerful cosmological simulations don't just predict the formation of massive galaxies like the Milky Way. They also predict that these giants should be surrounded by a vast entourage of thousands of smaller dark matter clumps called subhalos. Many of these predicted subhalos are tremendously massive and dense, with such strong gravity that forming stars and becoming visible dwarf galaxies should have been a foregone conclusion. This is the heart of mystery number 4, a problem so striking it earned the dramatic name, the too big to fail problem. The name itself is a clever nod to the 2008 global financial crisis, where certain massive banks were deemed too big to fail, meaning their collapse would be catastrophic for the entire system. In cosmology, the phrase refers to these largest subhalos around the Milky Way. They contain so much dark matter that their gravitational pull is overwhelming. They are simply too massive and too gravitationally powerful to have failed at the basic task of galaxy formation. Their sheer size should have easily drawn in enough gas to birth billions of stars, making them some of the brightest and most obvious satellite galaxies in our sky. Yet, when we take a census of the dwarf galaxies actually orbiting the Milky Way, we find a startlingly empty throne room. The observed dwarf galaxies are far fewer in number, and crucially, they are all much less massive and dense than the simulated subhalos that are supposedly their hosts. The most massive subhalos our simulations create have no visible counterparts at all. It's as if our theory predicts a bustling metropolis of bright cities, but when we look, we find only a few small, dim villages with the grandest capitals completely missing. This discrepancy forces us to confront a critical question. Where did all these massive dark matter clumps go, and why are they so dark? Scientists have pursued two main avenues to solve this cosmic case of the missing giants. The first possibility places the blame on the complex physics of ordinary matter. Even a massive dark matter subhalo needs to collect and cool gas to form stars and become visible. Perhaps incredibly powerful supernova explosions in the early universe, or the intense radiation from the first stars, blasted the gas right out of these smaller halos. Without gas, there can be no stars, and without stars, the massive subhalo remains forever dark and invisible to our telescopes. This process, known as astrophysical feedback, could have essentially sterilized these large subhalos, preventing them from ever lighting up. The other, more provocative possibility is that the fault lies not with the ordinary matter, but with our understanding of dark matter itself. The standard model of cosmology, known as lambda cold dark matter, assumes that dark matter is cold, meaning it moves slowly, and collisionless, meaning particles pass right through each other and only interact via gravity. But what if that's not entirely true? If dark matter particles had a small ability to interact with each other through some unknown force, they could diffuse away from the centers of these small halos, making them less dense and therefore less effective at gravitationally attracting gas. Alternatively, if dark matter was ever so slightly warm, meaning the particles had a small amount of intrinsic motion, this could prevent the smallest and densest clumps from forming in the first place. This warm dark matter scenario would suppress small-scale structure, potentially explaining the lack of the largest subhalos. The too big to fail problem is more than just a counting error. It's a direct challenge to the very framework we use to understand the universe's structure. Lambda-cold dark matter has been spectacularly successful at explaining the cosmos on the largest scales, from the cosmic microwave background to the distribution of galaxy clusters. But this problem, along with the core cusp issue, suggests it might be incomplete on the scale of individual galaxies and their satellites. Solving it requires us to look deeper into the chaotic physics of galaxy formation, or to dare to rewrite the fundamental properties of the universe's most dominant material. Each missing dwarf galaxy is a silent clue, pointing toward a richer, more complex cosmic story than we have yet written. Just when we thought the satellite galaxy puzzle couldn't get any stranger, a new layer of mystery emerges, one that seems to defy the very foundations of our cosmological models. If the invisible hand of dark matter guides the formation of structure, its work should be statistically elegant and random, a beautiful chaos governed by gravity alone. But what we find instead appears oddly organized, even artistic. This brings us to mystery number 5, the perplexing planes of satellite galaxies. Our standard model of cosmic evolution, lambda-cold dark matter, paints a very specific picture of how large galaxies like our Milky Way come to be. They grow over billions of years through a process called hierarchical merging, consuming countless smaller galaxies and dark matter clumps that approach from all directions. Think of it like a giant sphere slowly gathering asteroids from every point in space. Because these mergers are chaotic and come from random angles, the satellite galaxies that survive this process should eventually settle into a roughly spherical, swarming distribution around their host galaxy. They should orbit in all different directions with no preferred plane or alignment, much like a swarm of bees around a hive. Our most sophisticated supercomputer simulations consistently confirm this expectation, showing a disorganized, puffy cloud of satellites. Yet, when astronomers began to meticulously map the real satellites around our Milky Way and our nearest giant neighbor, the Andromeda Galaxy, they were met with a sight that was shockingly discordant. The satellites weren't scattered randomly at all. Instead, they were arranged with an almost architectural precision into vast, thin, rotating planes. Around the Milky Way, most of its known dwarf galaxies lie in an enormous, disk-like structure, a great sheet that is perpendicular to the galactic disk itself. Even more stunningly, these satellites aren't just sitting in a plane. They are coherently moving, streaming along in the same direction like cars on a cosmic freeway. The situation around Andromeda is, if anything, even more pronounced. There, astronomers have identified a vast, thin plane of satellites, many of which are orbiting in concert around the giant galaxy's pole. This discovery is profoundly problematic. It's not just that the simulations predicted a swarm and we see a disk. It's that such a thin, rotating structure should be incredibly short-lived. The gravitational tug from the host galaxy and from the satellites themselves should have sheared these delicate planes apart over a few billion years. The fact that we see them today, not just around one galaxy but two of the largest in our local universe, suggests they are either very recent formations, which would be a wild coincidence, or they are being somehow held together, which current physics cannot explain. So how do we resolve this contradiction between the predicted chaos and the observed coherence? Scientists are exploring several fascinating and some radical possibilities. One idea is that these satellite galaxies aren't the primordial, dark matter-dominated objects we assume they are. Perhaps they are tidal dwarf galaxies. These are second-generation galaxies born from gas and stars ripped out during a violent collision between two larger galaxies. This gas, already rich with heavy elements, could collapse to form new dwarf galaxies that would naturally inherit the orbital motion of the material ejected from the collision, placing them all in the same plane. The problem with this elegant solution is that tidal dwarfs should contain very little dark matter, whereas the motions of the satellites in these planes suggest they are still embedded within massive dark matter subhalos. Another, more profound possibility is that this is not an anomaly of matter, but a failure of gravity itself. Theories like modified Newtonian dynamics, or MUND, which propose tweaking the laws of gravity to explain galactic rotation curves without dark matter, can naturally produce such planes of satellites. In a MONDIAN universe, the gravitational field of the host galaxy could orchestrate the orbits of its satellites into a coherent disk. While MUND has its own significant challenges on larger cosmological scales, it highlights how the satellite plane problem forces us to question our most basic assumptions. The most conservative explanation, though statistically uncomfortable, is that we are simply seeing a rare fluke. Perhaps the Milky Way and Andromeda are cosmic oddballs, and their beautiful planes are just a temporary alignment in an otherwise random universe. But as our telescopes peer deeper, finding similar structures around other distant galaxies, the fluke argument becomes harder to maintain. The planes of satellites stand as a stark, elegant reminder that the universe often prefers patterns to chaos, and that our darkest mysteries might be hiding in plain sight, written in the organized motion of the smallest galaxies. Even as we grapple with the large-scale structure of dark matter halos, a more intimate and subtle mystery emerges from within the galaxies themselves. For decades, the flat rotation curve has been the cornerstone evidence for dark matter's existence, the observation that stars at the edge of a galaxy orbit just as fast as those near the center. It's a powerful, universal signal, but what happens when we stop treating all galaxies as a single, uniform class and start looking at them as individuals? This brings us to the surprising and nuanced puzzle of mystery number 6, the diversity problem in galaxy rotation curves. The logic seemed straightforward. If the gravity from the visible, baryonic matter, the stars and the gas, is the sole driver of a galaxy's rotation, then two galaxies with identical distributions of this visible mass should have identical rotation curves. Their stars should orbit at the very same speeds. Dark matter in the standard model is the invisible sculptor that makes up the difference. So it stood to reason that if the baryonic content is the same, the dark matter halo should also arrange itself in a similar way to provide the necessary extra gravity, resulting in a predictable matching rotation curve. It's a clean, almost mechanical expectation. However, the data from extensive surveys, most notably the Spitzer photometry and accurate rotation curves, or SPARC, database, has delivered a startling revelation. When astronomers compared galaxies with nearly identical amounts of stars and gas, they found that their rotation curves were wildly different. Some galaxies showed the expected strong dark matter dominance, with rotation speeds staying high far out into the outskirts. Others, with the exact same luminous mass, had rotation curves that plummeted, indicating a much weaker or less concentrated dark matter presence. The dark matter halo, it seems, is not a simple, predictable add-on that scales directly with the visible matter. There is a complex and unpredictable relationship at play, a conversation between light and dark that we are only just beginning to hear. This diversity problem forces us to consider that the history of a galaxy might be written not just in its stars, but in the very response of its dark matter halo. One compelling explanation points back to the Chinese letter OF ordinary matter. Galaxies are not static. They are dynamic ecosystems where bursts of star formation and the cataclysmic explosions of supernova inject enormous energy into the system. This energy can literally push the dark matter around. In a galaxy with a very active, bursty star formation history, these repeated blasts of feedback could have physically expanded the dark matter halo, making it less dense and thus less effective at accelerating orbiting stars. A quieter galaxy with a more sedate history of star birth would have left its dark matter halo undisturbed, allowing it to remain dense and dominant. In this view, the diversity of rotation curves is a fossil record of a galaxy's unique and turbulent life story. Yet another layer of complexity arises from the initial conditions of the dark matter itself. Perhaps the halos formed with an intrinsic diversity in their central densities, a natural variation set in motion by the tiny quantum fluctuations in the early universe that were then amplified by inflation. Maybe the specific way a halo assembled itself through a series of particular mergers with other smaller halos left each with a unique internal structure that now manifests in its rotation curve. This would mean that dark matter halos, much like galaxies themselves, have their own personalities and histories. The most radical interpretation of this data is that it isn't about dark matter's behavior at all, but rather a sign that our fundamental understanding of gravity is incomplete. Proponents of modified Newtonian dynamics, or MND, have pointed to the diversity problem as a key weakness of the dark matter paradigm. If dark matter is a single, universal particle, they argue, its behavior should be predictable and consistent. The fact that it isn't, they suggest, indicates that we are trying to patch a flawed theory of gravity with an invisible substance that must be endlessly tweaked to fit new observations. From the MND perspective, the diversity might instead stem from the subtle influence of a galaxy's external gravitational field, an effect known as the external field effect, which can alter the predicted rotation speeds without any dark matter. Resolving the diversity problem is like trying to understand why two children, raised in the same neighborhood and going to the same school, grow up to have completely different personalities. Is it nature or is it nurture? For galaxies, is the diversity in their dark matter halos an innate property they were born with, or is it a consequence of their life experiences, the stellar feedback and mergers that shaped them? Untangling this requires a new generation of ultra-high-resolution simulations that couple the physics of dark matter with the messy, complex astrophysics of gas, stars, and black holes. It also demands ever more precise observations to map the rotation of galaxies and reconstruct their detailed histories. This mystery reminds us that the universe prefers intricate relationships to simple rules, and that the dark side of the cosmos may hold more individuality than we ever suspected. But if the mysteries within individual galaxies challenge our understanding of matter, a far grander discrepancy is emerging from the very fabric of the cosmos itself, one that threatens the foundational parameters of our entire standard model of cosmology. This brings us to one of the most significant and hotly debated puzzles in modern astronomy, the Hubble tension. At its heart, this is a story about two different ways of measuring the universe's expansion rate, a value known as the Hubble constant. And these two methods, both exquisitely precise, are stubbornly refusing to agree. One method looks back to the very beginning, to the infant universe. By studying the cosmic microwave background, that faint afterglow of the Big Bang with satellites like Planck, we can see the imprint of the early universe's geometry and composition. This pristine snapshot allows us to run the cosmic film forward, using our well-tested model of physics to predict how fast the universe should be expanding today. This early universe measurement gives us a very specific, reliable value. The other method measures the expansion rate directly in our own cosmic neighborhood. Astronomers use incredibly reliable cosmic mile markers like Cepheid variable stars and Type Ia supernova. These are standard candles objects whose intrinsic brightness we know. By measuring how bright they appear to us, we can calculate their distance with fantastic accuracy. Then, by measuring their redshift, how much their light is stretched by the expansion of space, we get a direct local measurement of the Hubble constant. The problem is this: the local universe measurement consistently gives a faster, higher expansion rate than the prediction from the early universe. It's as if you meticulously planned a road trip using a map, calculating you should be driving 60 miles per hour to arrive on time. But then you glance at your speedometer and it reads 70. Both your map and your speedometer are trusted instruments, yet they disagree. One of them must be wrong, or perhaps there's something about the road itself you didn't account for. This isn't a small margin of error. The discrepancy stands at around 5.6 sigma, a level of statistical significance that in most fields of science would be considered a definitive discovery. This tension suggests a fundamental flaw in our understanding. So where does dark matter fit into this? The period between the release of the CMB and the formation of the first stars is known as the cosmic dark ages, a time when the universe was dominated by dark matter and neutral hydrogen. If dark matter possesses unknown properties or interactions that we haven't accounted for, if it could decay, interact with itself, or even interact with dark energy in a new way, it could have subtly altered the expansion history of the universe during this opaque epoch. Such new physics in the dark sector could have provided an extra nudge to the expansion rate, explaining why our local measurement is higher than the early universe prediction. Alternatively, this tension might force us to re-examine dark energy itself. Perhaps it is not a constant vacuum energy as in the simplest model, but a dynamic force that has evolved over time, growing stronger in more recent cosmic epochs and accelerating the expansion faster than anticipated. Or, in the most radical scenarios, it might point toward a need to modify Einstein's theory of gravity on the largest scales. The implications of this unresolved tension are enormous. If it persists, it means our standard cosmological model, lambda cold dark matter, is incomplete. We may be on the verge of discovering entirely new physics governing the dark components of the universe. The quest for resolution is now at the forefront of astronomy. The James Webb Space Telescope is turning its powerful infrared gaze toward the same cosmic mile markers, observing Cepheids and supernova with unprecedented precision to check and recheck the local measurement, free from the calibration uncertainties that plagued previous telescopes. Next-generation observatories will push these measurements even further, and new surveys of the large-scale structure of the universe will provide independent cross-checks. The Hubble tension is more than a technical disagreement. It is a beacon illuminating a potential crack in our cosmological model and guiding us toward a deeper, more complete theory of the cosmos. While we grapple with the universe's expansion on the grandest scales, another profound mystery lies hidden in the microscopic recipe of the cosmos itself, written in the first few minutes after the Big Bang. This is mystery number 8, the cosmological lithium problem. It's a tale of exquisite prediction, frustrating observation, and the tantalizing possibility that dark matter itself may have tampered with the universe's earliest chemistry. Our story begins in the searing heat of the primordial universe, mere minutes after its birth. During this brief, frenzied epoch known as Big Bang nucleosynthesis, the entire cosmos was a fusion reactor, hot and dense enough to forge the first atomic nuclei from a soup of protons and neutrons. The standard model of particle physics and cosmology allows us to calculate, with breathtaking precision, exactly how much of each light element should have been cooked up during this process. For 2 of the 3 primary elements, hydrogen and helium, the predictions match the observed abundances in the oldest, most pristine regions of the universe almost perfectly. This spectacular agreement is one of the cornerstone pieces of evidence for the Big Bang theory. But for the 3rd light element, lithium-7, the numbers simply do not add up. Our best theories predict about 3 times more lithium than what we actually see when we look at the ancient atmospheres of stars in our galactic halo. which have preserved this primordial signature for over 13 billion years. It's a small discrepancy by cosmic standards, but for a theory that otherwise works with such incredible accuracy, it's a glaring and persistent thorn. For decades, astrophysicists have searched for a conventional astrophysical solution. Perhaps these ancient stars have some unknown way of destroying lithium in their atmospheres over time. Maybe our understanding of stellar physics is incomplete, and the nuclear processes inside these old stars have somehow processed the lithium away. Yet, despite every effort, no ordinary stellar mechanism has been able to fully account for the missing lithium. This has led physicists to consider a far more radical explanation, that the culprit isn't ordinary matter at all, but the mysterious dark matter that permeated the early universe. This is where the puzzle transforms from a chemical anomaly into a potential window into dark matter's nature. The key insight is timing. Big Bang nucleosynthesis was an incredibly delicate process, a runaway nuclear reaction that lasted only a few minutes before the expanding universe cooled and froze it in place. The final abundances of those light elements are exquisitely sensitive to the conditions during that brief window: the density of particles, the temperature, and the rate of expansion. If a new type of particle were present, injecting energy or interacting with the primordial soup, it could have dramatically altered the outcome. This is precisely what some dark matter models propose. Imagine a scenario where dark matter is not completely stable. Certain theoretical models suggest that in the universe's first minutes, dark matter particles could have been annihilating with each other or decaying into standard model particles. This process would have released a flood of energy: protons, neutrons, electrons, and photons right into the heart of the nucleosynthesis process. This sudden injection of energy and particles would have disrupted the carefully balanced chain of nuclear reactions. It could have provided more targets for nuclear fusion, altered the balance between protons and neutrons, or even broken apart freshly forged lithium nuclei as quickly as they formed. In some models, this dark matter intervention efficiently destroys just enough lithium-7 to bring the theoretical predictions into perfect alignment with what we observe, without disturbing the perfect agreement we have for hydrogen and helium. It's a cosmic surgical strike performed by an invisible hand in the universe's first 3 minutes. The lithium problem, therefore, becomes a unique and powerful laboratory. It's not a mystery we probe with gigantic underground detectors or vast telescopes, but with ultra-precise nuclear physics and cosmology. By refining our measurements of the primordial abundances of not just lithium, but also deuterium and helium to even greater precision, we can tightly constrain the possible properties of any dark matter particle that might have been active during nucleosynthesis. We can essentially rule out entire classes of dark matter models that would have perturbed the element abundances too much, while guiding us toward those that provide a perfect fit. Future observations from the next generation of giant telescopes promise to track down even more pristine second-generation stars, whose atmospheres hold the untarnished record of the universe's first elements. If a consistent lithium deficit is confirmed across countless ancient stars, the case for an exotic, early interacting dark particle will grow immensely strong. This tiny discrepancy in the amount of a single element serves as a profound reminder that the effects of dark matter may not be limited to the gravitational realm. Its influence might be written into the very atoms that make up our bodies and our world. Solving the lithium problem could do more than just complete our picture of the Big Bang. It could reveal that dark matter was an active participant in the creation of the elemental building blocks of everything we see. While we can look to the ancient stars for clues about the universe's first minutes, another groundbreaking experiment aimed its antennae at an even more profound silence: the period before the first stars ever switched on. This era, known as the Cosmic Dawn, is a pivotal chapter in our history, and a startling signal from its depths has presented us with mystery number 9, the perplexing 21-centimeter absorption signal anomaly. To understand why this is such a big deal, we need to step back into that dark age. For millions of years after the Big Bang, the universe was a vast, expanding cloud of neutral hydrogen gas cooling in the aftermath of creation. This gas can emit or absorb radiation at a very specific wavelength, 21 centimeters. It's a hyperfine transition, a tiny energy shift in the hydrogen atom that creates a faint radio whisper. As the first stars and galaxies began to ignite, their intense ultraviolet light would have excited that primordial hydrogen, causing it to absorb background radiation at this 21-centimeter wavelength. We expect to see a dip, an absorption signal, in the radio spectrum from that era. The depth and shape of this dip are a cosmic thermometer, telling us about the gas's temperature and how quickly those first lights came on. In 2018, a small and unassuming radio antenna array called EDGES, located in the remote deserts of Western Australia, reported a detection of this signal. But what they found sent shockwaves through the cosmology community. The absorption dip was roughly twice as deep as the absolute maximum predicted by our standard models of cosmic dawn. It was an anomaly of stunning proportions. For the signal to be that deep, the hydrogen gas must have been significantly colder than anyone thought possible. The standard physics of the time simply doesn't allow for gas to cool to such extremes. It's as if we found a cup of coffee that had been sitting out overnight, but instead of being room temperature, it was nearly frozen. Something or someone had to have put it in the freezer. This is where dark matter enters the scene with a breathtakingly elegant, if unproven, solution. What if the primordial hydrogen was cooled by interacting with the dark matter that surrounded it? In the standard model, dark matter and ordinary matter are ships passing in the night. Their only interaction is through gravity. But if dark matter particles had a small, non-gravitational interaction with protons, if they could, in a sense, collide with and transfer energy to the hydrogen atoms, they could have acted as a cosmic heat sink. The dark matter, which is naturally cold, could have siphoned thermal energy away from the hydrogen gas, chilling it far beyond what was thought possible and creating the extraordinarily deep absorption signal that EDGES observed. This would be our first direct evidence of dark matter interacting with normal matter through any force other than gravity, a monumental discovery that would shatter the standard WIMP paradigm and open up a whole new field of physics. Of course, a claim this extraordinary requires extraordinary evidence, and the scientific community has responded with intense scrutiny. The primary alternative explanation is that the signal itself is not cosmological, but an artifact of the instrument or our environment. The EDGES antenna was measuring an incredibly faint signal against a roar of foreground radio noise from our own galaxy, which is millions of times brighter. Extracting the cosmic signal requires subtracting this foreground with near-perfect precision. Critics have argued that an imperfect subtraction model could easily produce a fake, deep absorption feature. Others have suggested more unconventional astrophysical sources, such as an excess of radio background radiation from the earliest galaxies themselves, which could also make the absorption appear deeper against a brighter backdrop. However, follow-up analyses have so far failed to definitively rule out the EDGES result, keeping the dark matter interpretation alive and simmering. The ultimate verdict will not come from a single small antenna, but from a new generation of colossal radio telescopes designed specifically to map the cosmic dawn. Projects like the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the Future Square Kilometre Array, or SCAR, are now coming online. These are vast fields of antennas that will measure the 21-centimeter signal with unprecedented sensitivity, and crucially, will be able to cross-check their results against each other. They won't just look for a single global signal, they will map its fluctuations across the sky, building a three-dimensional map of the infant universe's temperature. If they confirm an absorption signal as deep as Edges reported, it will be a paradigm-shifting moment, forcing us to accept that dark matter is not the aloof, ghostly substance we imagined, but an active participant that helped shape the conditions for the very first stars to form. If they find a more standard signal, the Edges result will fade into history as a fascinating false alarm. Either way, the hunt for this signal has already proven its value, pushing our technology and our imagination to their limits in the quest to listen in on the universe's first whispers. Yet this grand discrepancy between what our models predict and what our telescopes reveal is not the end of the story. It is the beginning of an even deeper and more focused quest. If the theory is correct and thousands of these dark matter clumps are truly there, then the vast majority of them must be completely dark. They are halos of pure, pristine dark matter that, for reasons we are still trying to understand, never manage to attract or retain the gas needed to spark star formation. They are the cosmic ghosts, invisible islands in the vast sea of our galaxy's dark matter halo. This prediction transforms the missing satellites problem from a failure of the model into its most audacious and testable claim, that a hidden population of invisible structures surrounds us, and finding them would be the ultimate validation of our understanding of the dark universe. So how do you hunt for something that emits no light? Astronomers have become cosmic detectives, developing ingenious methods to infer the presence of these dark satellites through their subtle, gravitational effects on the things we can see. One powerful technique is gravitational lensing. As the immense gravity of a dark matter subhalo drifts between us and a distant background galaxy, it can warp and distort the galaxy's light, creating a telltale, though incredibly faint, anomaly in the lensed image. It's like looking for the ripples on the surface of a pond to find the invisible fish swimming just beneath. While this method has had some success in detecting massive subhalos around distant galaxies, finding the much smaller Earth mass halos predicted around our own Milky Way is a monumental challenge that will require the next generation of ultra-sensitive space telescopes. A more promising method for our local galactic neighborhood involves watching for gravitational disturbances in the delicate traces of our galaxy's history. Throughout its life, the Milky Way has cannibalized smaller dwarf galaxies. As these galaxies are torn apart by our galaxy's tidal forces, they leave behind long, thin ribbons of stars known as stellar streams. These streams are exquisite gravitational sensors. If a dark, massive subhalo passes near one of these streams, its gravity will tug on the stars, perturbing the smooth flow and creating a visible kink or gap in the ribbon. By meticulously mapping these streams with observatories like the Gaia spacecraft, astronomers are essentially turning the sky into a gigantic dark matter detector, watching for the telltale tremors that signal the passage of an unseen object. There is a third, more speculative hunt underway, one that looks not for gravity's effect, but for the potential self-destruction of dark matter. If dark matter particles are their own antimatter counterparts, then wherever dark matter is exceptionally dense, like in the core of these subhalos, particles could occasionally collide and annihilate, transforming their mass into energy and producing a flash of gamma rays. Telescopes like the Fermi Gamma Ray Space Telescope have spent years scanning the sky, looking for these unexplained point sources of high-energy radiation that could be the funeral pyres of dark matter particles. While no definitive signal has been found, each potential candidate drives a feverish burst of analysis and follow-up. What we learn from this search will fundamentally shape our cosmic story. If we conclusively find this population of dark, starless halos, it will be a spectacular triumph for the lambda cold dark matter model. It would confirm that our understanding of dark matter's gravitational behavior is essentially correct, and that the solution to the missing satellites problem lies in the complex astrophysics of gas cooling and star formation, not in the fundamental nature of dark matter itself. However, if even these most sensitive searches come up empty, the implications are profound. it would suggest that our simulations are over-predicting the number of small-scale structures, a failure that would point directly to the properties of dark matter. Such a null result would be powerful evidence for a warmer, more exotic type of dark matter particles with a small amount of intrinsic motion that would prevent the very smallest clumps from ever forming in the first place. The silent, dark frontiers of our own galaxy hold the answer to whether the universe's dominant matter is cold and structured or warm and smooth, a mystery whose solution is hiding in plain sight, or more accurately, in perfect darkness. But if these invisible threads of dark matter create the cosmic web, then the empty spaces between them, the great cosmic voids, should be truly barren, right? According to our best simulations, these vast, empty regions aren't completely empty. They should still contain a sparse population of faint, lonely galaxies, and more importantly, a tenuous web of dark matter itself. Yet, when we point our telescopes at the real universe, we find something deeply puzzling. Some of these voids appear far emptier than they have any right to be. This is mystery number 11, the void phenomenon, a profound emptiness that challenges our understanding of how the dark universe evolves. Picture the largest structures in the cosmos not as collections of matter, but as a hierarchy of emptiness. Voids are the cavernous bubbles in the foam of the cosmic web, some spanning hundreds of millions of light-years across. In the standard lambda cold dark matter model, these regions do contain matter, just far less of it. The gravity from the surrounding walls and filaments of the web should pull a certain number of galaxies and dark matter into even the deepest voids. Our simulations are very specific about this. They predict a minimum density, a floor below which the void should not fall, but observations tell a different story. By counting galaxies and mapping the gravitational pull within these voids, astronomers have found that some are startlingly underpopulated. They are emptier by a significant margin than the simulations allow. It's as if we predicted a desert should have a few hardy shrubs and cacti scattered about, but when we arrive, we find nothing but bare, windswept sand stretching to the horizon. This excessive emptiness points to a potential flaw in our model of the dark sector. One compelling possibility is that we are witnessing an unexpected dialogue between the two great unknowns, dark matter and dark energy. Dark energy, the force driving the accelerated expansion of the universe, is often treated as a smooth, constant background energy, but what if it's more dynamic? If dark energy were stronger in these underdense regions, it could act as a repulsive force, effectively pushing out any remaining matter and evacuating the void to a degree our models don't account for. Alternatively, the dark matter itself might possess unknown properties. If dark matter particles can interact with each other through a force other than gravity, a phenomenon known as self-interacting dark matter, this could generate a pressure that prevents them from collapsing into the very smallest halos within the void. Without these small dark matter clumps to act as gravitational seeds, galaxies would never form, leaving the void starkly empty. The void phenomenon also provides a unique testing ground for theories that seek to do away with dark matter entirely. Modified gravity models like modified Newtonian dynamics or its relativistic cousin, tensor vector scalar gravity, make a different set of predictions for how matter should behave in extremely low-density environments. In these theories, the laws of gravity themselves are different where the gravitational field is very weak. This could naturally explain why the voids are so empty. Without the need for dark matter to begin with, there's simply less total matter to be pulled in. The gravitational force in these vast empty spaces might fall off faster than Newtonian or Einsteinian gravity predicts, resulting in the observed lack of structure. While these models face their own significant challenges on other scales, the void phenomenon is one area where they might actually provide a more elegant solution. Resolving this mystery requires a new kind of cartography, not of the bright structures, but of the dark, empty spaces between them. This is the primary mission of a new generation of space telescopes like Euclid and the Nancy Grace Roman Space Telescope. These aren't just cameras, they are cosmic archaeologists designed to map the distribution of galaxies and dark matter in 3 dimensions across an enormous swath of the universe. By observing billions of galaxies, they will allow us to identify and catalogue thousands of these cosmic voids, measuring their shapes, sizes, and internal densities with unprecedented precision. Most importantly, they will use the subtle warping of light from background galaxies, a technique called weak gravitational lensing, to weigh the dark matter within these voids directly. For the first time, we will have a clear census of nothingness. Will the day to show that the voids contain the faint trace of dark matter our standard model predicts? Or will they confirm the unsettling emptiness, forcing a radical rewrite of our understanding of the dark universe? The answer lies in the deepest voids, waiting to be filled not with matter but with meaning. Just as the vast cosmic voids present a puzzle of profound emptiness, the universe offers a counterpoint in a class of objects so faint they were almost overlooked entirely. These are the ultra-diffuse galaxies, or UDG, and their discovery has unveiled one of the most baffling dichotomies in modern astronomy. Mystery number 12, the perplexing dark matter halos of these galactic ghosts. Imagine a galaxy the size of the Milky Way with its hundreds of billions of stars. Now remove 99% of those stars, spreading the remaining 1% out into a vast, ethereal haze so thin you could look right through it. That is an ultra-diffuse galaxy. For decades, they slipped through the nets of our surveys, their light so faint and spread out they blended into the background. But with the advent of powerful new telescopes like the Dragonfly Telephoto Array, designed specifically to see extremely low surface brightness objects, hundreds of these spectral cities have been found, primarily orbiting within the dense environments of galaxy clusters. The initial assumption was that these wispy, fragile-looking galaxies must be just that, fragile. With so few stars, it stood to reason they must be devoid of dark matter, their tenuous grip on reality easily shattered by the gravitational tides of their massive cluster neighbors. But when astronomers pointed their spectrometers at these ghosts to measure the motions of their stars, they were met with a result so shocking it defied all intuition. Some of these ultra-diffuse galaxies, against all odds, were among the most dark matter-dominated objects ever discovered. Galaxies like Dragonfly 44 in the Coma cluster has a mass almost indistinguishable from the Milky Way, yet its stellar content is less than 1% of our galaxies. It is a colossal sphere of pure, unseen mass with a mere sprinkling of stars on top. Its dark matter halo is so immense and dense that it should not have been possible for galaxy formation to have failed so spectacularly within it. It is a cosmic paradox, a heavyweight champion masquerading as a featherweight, but the plot thickens dramatically. For every ultra-diffuse galaxy like Dragonfly 44 that is teeming with dark matter, there appears to be another, visually identical cousin that possesses almost none. These dark matter-free UDGs present an equal and opposite challenge to our theories. How can two galaxies that look so similar, same size, same luminosity, same apparent fragility, have such radically different underlying natures? One is a titan of dark matter, a failed galaxy that somehow acquired a massive halo but never formed many stars. The other appears to be a tidal dwarf galaxy, a shred of stars and gas torn loose during a violent galactic collision that simply does not have a dark matter halo of its own. This extreme diversity is not a minor footnote. It is a direct assault on our understanding of the fundamental connection between dark matter and the galaxies that light up within it. This puzzling dichotomy forces astrophysicists to consider wildly different origin stories for these enigmatic objects. The dark matter-rich UDGs are perhaps the most intriguing. One leading theory posits they are failed galaxies. They may have formed within completely normal, massive dark matter halos in the early universe. But due to their location in the harsh environment of a cluster, their gas, the raw fuel for star formation, was violently ripped away. A process called ram pressure stripping, where the intracluster plasma acts like a powerful cosmic wind, could have scoured the galaxy clean before it had a chance to form the vast majority of its stars, leaving behind a massive dark matter halo populated by only a few early stellar generations. Alternatively, incredibly strong supernova feedback in their youth could have blown out their gas, permanently quenching star formation and leaving them in a state of arrested development. On the other side of the coin, the dark matter poor UDGs demand a completely different explanation. The most compelling is that they are indeed tidal dwarf galaxies. When two large gas-rich galaxies collide, their gravitational dance can fling out massive tails of gas and stars that are no longer bound to the dark matter halos of the parent galaxies. This ejected material, composed purely of baryonic matter, can then collapse under its own gravity to form a new, dark matter-free galaxy. These objects would be born looking old and diffuse, having never been through the traditional, slow process of hierarchical growth within a dark matter halo. Their existence is a direct prediction of this violent formation channel, and finding them is a crucial piece of evidence. The existence of these two extreme populations living side by side is a gift and a curse for cosmologists. It is a curse because it introduces a stunning level of complexity into the galaxy formation playbook, showing that appearance alone is a terrible indicator of an object's true mass and history. But it is a gift because it provides a unique laboratory. By studying the two types in tandem, we can isolate the specific role dark matter plays. The dark matter-rich UDGs show us what a galaxy looks like when dark matter is entirely in control, a pure demonstration of its gravitational influence. The dark matter-free UDGs show us what a galaxy can look like when it is built by the laws of hydrodynamics and gravity alone, free from the shadow of a dark matter halo. This comparison allows us to run a controlled experiment, teasing apart the individual contributions of dark and normal matter to the galaxy we see. Ultimately, the story of ultra-diffuse galaxies is a story of extremes. They represent the outer boundaries of what is possible in galaxy formation, pushing our models to their breaking point. Their discovery tells us that the universe has more than one way to build a galaxy that looks faint and diffuse, and that the relationship between the luminous and dark universes is far more complex and nuanced than a simple one-to-one mapping. Even as we encounter stunning diversity in the rotation curves of some galaxies, a counterintuitive and deeply mysterious uniformity emerges from their very hearts. Across the cosmos, from the tiniest dwarf galaxies to the most massive ellipticals, astronomers are finding that the dark matter density in their inner regions follows a surprisingly universal profile. This is not the wild variation we saw in the outer rotation curves. This is a cosmic constant, a fundamental rhythm that all dark matter halos seem to obey, regardless of their size, history, or the amount of visible matter they contain. This strange harmony is mystery number 13, a profound clue that the dark universe may operate by a simpler set of rules than our most complex simulations can currently capture. This universal profile is often described by a simple mathematical relationship known as a Navarro-French-White, or NFW, profile, named after the scientists who first identified it in simulations. It describes a halo whose density increases steadily and predictably towards the center without ever becoming infinitely dense. For years, this was considered a triumphant prediction of the cold dark matter model. Gravity, acting on a collisionless fluid, should naturally sculpt halos into this universal form. But the real surprise came when observers, armed with ever more precise data, began to test this prediction in the real world. They found that an astonishing range of galaxies, from those brimming with stars to those that are nearly barren, all show dark matter distributions in their cores that align with this same basic profile. It's as if galaxies with completely different life stories, some born in violent mergers, others in quiet isolation, some with furious star formation, others dormant for eons, all decided to organize their dark matter in exactly the same way. This is not what anyone expected. A galaxy's formation history is incredibly violent and complex, shaped by mergers, bursts of star formation, and the explosive feedback from supernova and black holes. This tumultuous baryonic activity should have left an indelible imprint on the dark matter, stirring it up, pushing it around, and creating a wild diversity of central densities. The fact that we see such a quiet, universal consistency is a quiet revolution. This discovery presents a fascinating tension with the other dark matter mysteries we've explored. On one hand, we have the diversity problem in rotation curves, which suggests that the relationship between dark and light matter is complex and unpredictable. On the other, we have this universal density profile, which suggests a surprising simplicity and resilience in the dark matter's core structure. Reconciling these two facts is one of the great challenges in modern astrophysics, and theorists have put forward several compelling and competing ideas. The first possibility is that dark matter is not as simple and aloof as we thought. The concept of self-interacting dark matter has gained traction as a potential solution. If dark matter particles can collide with one another through some unknown force, these interactions could act as a form of energy transfer, smoothing out irregularities and driving the halo back towards a stable, universal equilibrium shape. It would be a self-correcting mechanism, a thermostat for the dark universe that erases the complex history written by baryonic physics and enforces a simple, fundamental order. The second major possibility flips the script entirely, suggesting that the very baryonic processes we thought would cause diversity are actually the engine of this uniformity. This is the concept of baryonic feedback as a universal sculptor. The idea is that the incredibly violent energy injection from supernova and active black holes doesn't just randomly churn the dark matter. It does so in a predictable, cyclical way that actually forces the halo into the NFW profile. In this scenario, early bursts of star formation blow out gas, which temporarily reduces the gravitational pull in the center, allowing the dark matter to expand outward. Then, as the gas cools and falls back in, it drags the dark matter with it, concentrating it again. This repeated pumping action over billions of years could erase the initial conditions of the halo and drive it toward a universal endpoint regardless of its starting point. In this view, the simple dark matter profile is not a signature of dark matter's nature, but a fossil of the complex and repetitive astrophysical processes that shaped the galaxy. A third, more sobering possibility is that our simulations are still not capturing the full complexity of the real universe. The highest resolution simulations that model both dark matter and baryonic physics are among the most computationally expensive experiments ever conducted, and they still have to make simplifying assumptions about the messy details of star formation and feedback. It's possible that when we can finally simulate the entire life of a galaxy with perfect fidelity, this universal profile will naturally emerge as a consequence of physics we are already aware of, but are not yet modeling correctly. The universality may be a signpost pointing toward a deeper level of understanding in galaxy formation physics that we have not yet achieved. Resolving this mystery requires a new generation of observations that can probe the very centers of galaxies with exquisite detail. Dwarf spheroidal galaxies, which are overwhelmingly dominated by dark matter, are perfect laboratories because there is very little baryonic interference to confuse the signal. By measuring the precise motions of thousands of individual stars within these dwarfs, we can map the dark matter distribution right down to the central parsec. Similarly, the most massive galaxy clusters act as enormous gravitational lenses, and by studying how they distort the light of background galaxies, we can weigh their dark matter components with incredible precision. testing for deviations from the universal profile in these giant halos. The data now pouring in from observatories like the James Webb Space Telescope and the upcoming Vera-C Rubin Observatory will provide this crucial evidence, allowing us to stress test the universal profile across the entire spectrum of cosmic structure. The answer will tell us if the dark sector is simpler than we dreamed, or if the visible universe is far more effective at imposing its order on the dark. The universe is full of grand dances, but few are as intimate or consequential as the one happening right in our own cosmic backyard. The Milky Way is not alone. It is gravitationally bound to our giant neighbor, the Andromeda Galaxy, and a collection of smaller satellites forming what astronomers call the local group. For decades, we've known these two titans are destined to collide in a spectacular merger billions of years from now. But the precise choreography of their approach holds a subtle and telling clue, leading us directly to mystery number 14, the timing argument anomaly, a cosmic case where the clock seems to be ticking faster than the mass can explain. The principle behind this is beautifully simple. It's known as the timing argument, and it works a lot like calculating the trajectory of a thrown ball. If you see a ball at the peak of its arc, you can work backwards, by knowing its current position and velocity, and by applying the known laws of gravity, you can calculate exactly how long ago it left the thrower's hand, and crucially, you can estimate the strength of the throw. Now apply this to our galaxy and Andromeda. We can measure their current separation, and we can measure their radial velocity, the speed at which they are moving directly toward each other. The timing argument uses these two pieces of data, along with the laws of gravity, to ask a straightforward question. If these two galaxies started their lives at rest after the Big Bang and have been falling toward each other ever since, how much mass must be in the local group to pull them together at the observed speed and bring them to their current separation in exactly the age? Universe, the answer this calculation provides is startling. The mass required to make this simple model work is significantly larger than the total mass we can account for from all the visible stars and gas in both galaxies, plus all their estimated dark matter halos. It's as if we watched that ball's arc and calculated that the thrower must have been impossibly strong. The timing argument suggests there is a substantial amount of mass missing from our ledger of the local group, or that our fundamental understanding of this gravitational dance is somehow flawed. This discrepancy opens the door to several fascinating possibilities. The first and most obvious is that there is simply more dark matter out there than we have currently mapped. Our models of the Milky Ways and Andromeda's dark matter halos are based on certain assumptions about their density and extent. The timing argument anomaly could be telling us that these halos are far more massive and extensive than we think, reaching out with vast, tenuous skirts of dark matter that envelop the entire local group. This extra mass would provide the additional gravitational tug needed to accelerate the galaxies to their observed speeds. Alternatively, the missing mass could be hiding in plain sight as an unseen population of ultra-faint dwarf galaxies or even pure dark matter subhalos that have so far evaded our telescopes, all contributing their gravity to the system. However, the problem might not be missing mass, but an incorrect reading of the dance steps themselves. The classic timing argument makes a critical assumption that the Milky Way and Andromeda are on their first approach. But what if this isn't their first cosmic tango? Some simulations suggest a more complex history, one where the two galaxies may have had a close encounter billions of years ago, a gravitational slingshot that set them on their current collision course. If they have already swung past each other once before, their current high speed isn't just from a continuous fall from rest, it's a relic of that previous interaction. This would mean the simple timing calculation is based on a false premise, and no extra mass is needed to explain the observed velocity. The anomaly would then vanish, not because of dark matter, but because of a forgotten chapter in our galactic history. A third, more radical interpretation challenges the very laws governing the dance. For proponents of modified Newtonian dynamics, or MND, the timing argument isn't an anomaly, it's a prediction. MND proposes that in the extremely weak gravitational field that exists between two galaxies separated by millions of light-years, gravity behaves differently than Newton's or Einstein's laws predict. It becomes stronger. In a MONDIAN universe, the observed high speed of approach between the Milky Way and Andromeda is exactly what should happen with the known amount of visible mass, no dark matter required. For them, the timing argument is a success story for their model, not a problem to be solved. Resolving this decades-old mystery is no longer a matter of theoretical debate. It is now an observational priority, and the key to unlocking it is precision. The European Space Agency's Gaia mission is revolutionizing our understanding of this cosmic dance. By mapping the proper motion, the tiny sideways drift of stars in Andromeda with incredible accuracy, Gaia is providing the first full, three-dimensional velocity vector for our sister galaxy. We are no longer just measuring how fast it's coming toward us, we are learning its precise direction of travel through space. This data is the equivalent of getting a high-resolution video of the ball's arc instead of a single blurry photo. It will allow astronomers to run sophisticated simulations that can trace the orbits of both galaxies backwards in time with far greater confidence, testing the first encounter hypothesis against the missing mass hypothesis. Future observations will further tighten these constraints. The Nancy Grace Roman Space Telescope will conduct deep surveys to hunt for the ultra-faint dwarf galaxies that could account for the missing mass. And even more precise astrometric missions on the drawing board will continue to refine the velocity measurements. The story of the Milky Way and Andromeda is our story, the future of our own galaxy written in the motions of the stars. By deciphering the timing argument anomaly, we aren't just solving a local puzzle, we are conducting a critical test of gravity itself on an intergalactic scale, a test that will either reveal a hidden reservoir of dark matter, uncover a dramatic galactic history, or force us to rewrite the laws of physics. Yet, even as we look outward to the grand dance of galaxies, a more immediate and unsettling possibility emerges much closer to home, hidden within the familiar plane of our own Milky Way. This is mystery number 15, the dark matter disk hypothesis, and it proposes that our galaxy holds a secret, invisible mirror of itself, a second disk made not of stars but of dark matter, lying flat and vast within the stellar plane we know so well. The very idea challenges the standard view of dark matter halos as simple, puffy spheres enveloping galaxies. This new theory suggests that the dark sector might be far more structured and interactive than we ever imagined. The proposed mechanism for creating such a disk is both elegant and complex. Over billions of years, the ordinary matter of the Milky Way's disk, the vast clouds of gas and dust, has been swirling, collapsing, and clumping together to form stars. This constant churning motion generates powerful gravitational drag. If a fraction of the dark matter in our halo interacts with this dense, rotating ordinary matter, even just a little bit, it could have experienced a similar drag effect. Just as a spaceship passing through a planetary atmosphere slows down due to friction, these dark matter particles would have lost energy and angular momentum, causing them to sink out of the spherical halo and settle into a thinner, faster rotating disk aligned perfectly with the visible one. It's a process of gravitational sedimentation, creating a dense, pancake-like distribution of dark matter right here in our galactic neighborhood. This is not just a theoretical curiosity. A dark disk could resolve two significant and seemingly unrelated puzzles. The first involves direct detection experiments. For years, these ultra-sensitive underground labs have been searching for the telltale ping of a dark matter particle colliding with an atomic nucleus. Many experiments have reported tantalizing, low-energy signals that come and go with the seasons. The reasoning is that as Earth orbits the Sun, our planet should move through the galactic dark matter halo, with our speed relative to the halo changing throughout the year, creating an annual modulation in the expected signal. However, if a dense dark disk exists rotating along with the visible disk, then Earth's motion through it would be very different. Our solar system bobs up and down through the galactic plane, and this motion could create a much stronger and more complex modulation signal that might just explain the puzzling results from experiments like DAMA and co-GNT. A dark disk would provide a new, local source of dark matter that we are constantly plunging through. The second puzzle involves the delicate stellar streams we discussed earlier, those ribbons of stars torn from dwarf galaxies. The precise shapes of some streams, like the famous GD1 stream, show unusual gaps and wiggles that are difficult to explain with the smooth, spherical gravity of the standard halo alone. The gravitational tug from a dense, thin dark disk could provide just the right kind of perturbation to create these observed features, acting as a hidden spoon stirring the galactic pot. But does this intriguing hypothesis hold up to scrutiny? The evidence is a battlefield of competing data. On one side, studies of the dynamics of stars in the solar neighborhood, particularly their vertical motions perpendicular to the galactic plane, place tight constraints on the amount of unseen mass tugging at them. Too much mass in a dark disk would make the stars oscillate faster than we observe. These studies suggest that any dark disk must be less massive than some of the more optimistic models proposed, though a thin, dense disk with a modest mass has not been ruled out. Furthermore, incredibly precise measurements of the Milky Way's gravitational field, inferred from the slight warping of distant background galaxies, a technique called weak gravitational lensing, also struggle to find a clear signature of such a distinct flattened component. The lensing data currently favors a more traditional, nearly spherical halo. The ultimate verdict on the dark disk will come from a new era of galactic cartography. Missions like the European Space Agency's Gaia spacecraft are already revolutionizing our understanding. By precisely mapping the positions and motions of over 1 billion stars, Gaia is effectively conducting an ultra-sensitive gravitational survey of the Milky Way. As we gather more data, we will be able to detect the most subtle tugs on these stars, potentially revealing the faint but persistent gravitational signature of a dark disk pulling them ever so slightly as they orbit the galaxy. Future spectroscopic surveys will add the crucial third dimension of velocity, allowing us to build a dynamic model of the galactic gravitational field with unmatched precision. Finding a dark disk would be a paradigm-shifting discovery. It would mean that dark matter is not entirely aloof and non-interacting. It would suggest that the dark sector has a rich and complex physics of its own, capable of forming intricate structures through its relationship with ordinary matter. It would force us to rewrite the models for our home galaxy and reconsider the distribution of dark matter in all disk galaxies across the universe. The hunt for this hidden mirror within our own sky is a testament to how many cosmic secrets might still be hiding in the most familiar of places, waiting for us to learn how to see the darkness in a new light. But this elegant architecture of satellite galaxies presents a paradox that cuts to the very core of dynamical physics. According to our standard understanding of gravity, these vast, thin, rotating planes of satellites should be incredibly ephemeral structures. The gravitational pull of the massive host galaxy, combined with the mutual interactions between the satellite galaxies themselves, should have sheared these delicate disks apart over a few billion years. They are like spinning a plate on a stick. The slightest imbalance or external nudge sends it wobbling out of control. The fact that we observe these coherent structures today, not just around one galaxy but around the two largest in our local group, suggests they are either astonishingly young, a wild statistical fluke, or they are being somehow held together by a mechanism our current models cannot explain. This is the heart of the persistence problem, a direct challenge to our understanding of how dark matter halos are structured and how satellites evolve within them. The standard lambda-cold dark matter model predicts a halo that is predominantly smooth and spherical, with subhalos the homes of satellite galaxies orbiting in all directions. In this environment, any primordial plane of satellites would quickly disperse due to a process called differential precession. Imagine a handful of marbles rolling around a wide, shallow bowl. Each marble, depending on the specific angle and speed of its orbit, will have a slightly different path. Over time, their collective arrangement will dissolve into a random swarm. For a satellite plane around a galaxy, this gravitational mixing should erase all coherence within a cosmic eye blink, far less than the age of the universe. The continued existence of these planes implies that the dark matter halo itself may not be the simple, featureless sphere we assume. It might possess a degree of rigidity or a specific shape that helps to lock the satellites into their shared orbital plane, preventing the differential forces from tearing them apart. Alternatively, the dark matter particles might interact with each other in a way that provides a stabilizing influence, a subtle pressure that maintains the disk structure against the disassembling pull of gravity. Scientists are exploring several fascinating solutions to this dynamical puzzle. One compelling idea is that these planes are not ancient structures at all, but relatively recent acquisitions. Instead of individual satellites falling in randomly, perhaps entire groups of dwarf galaxies are being accreted together in a single, colossal event. If a small group of galaxies that already shared a common motion was captured by the Milky Way or Andromeda, they could retain their coordinated orbits for a longer period, appearing as a coherent plane today. This would solve the persistence problem by making the planes temporary, albeit common, features in a galaxy's life. However, this requires a steady supply of such infalling groups, and it remains to be seen if this is a frequent enough occurrence to explain the planes we see. A more profound solution involves rethinking the nature of dark matter itself. If dark matter is not completely collisionless but has a small ability to interact with itself, a property known as self-interacting dark matter, these interactions could generate a form of friction within the halo. This friction could dampen the orbits of the satellite galaxies, preventing them from precessing away from their common plane and effectively locking them into a stable, long-lived configuration. It would be as if the marbles in our bowl were rolling through a thin syrup, their motions coupled and their arrangement preserved. Another radical possibility is that we are seeing the fingerprint of modified gravity. Theories like WIMPs predict that the gravitational field of a disk galaxy can naturally give rise to stable, planar configurations of satellite orbits without the need for any dark matter at all. In this view, the persistence isn't a problem to be solved, it's an expected outcome. The path to resolving this mystery lies in measuring not just where these satellite galaxies are, but precisely how they are moving. This is the promise of a new generation of astronomical surveys, the Vera-C, Rubin Observatory's legacy survey of space and time, or LSST, will repeatedly scan the entire southern sky, tracking the minuscule proper motions of these faint dwarf galaxies over a decade. For the first time, we will have a real-time movie of their orbital dance. These precise measurements will allow us to trace their orbits backwards and forwards in time with incredible accuracy. We will be able to determine if their motions are truly coherent and stable, indicating a long-lived structure held together by unknown physics, or if they are on the verge of dispersal, revealing the planes as fleeting and recent additions to our galactic neighborhood. The answer will either cement our standard model of dark matter halos or force us to embrace a more complex and interactive dark sector, one where the invisible majority of matter can impose order on the cosmos in ways we are only beginning to imagine. If the universal dark matter profile suggests a cosmic constant, a hidden and far more dynamic process is at work within the smallest galaxies, one that appears to be rewriting their internal structure from the inside out. This is mystery number 17, the dark matter heating problem, and it reveals that the relationship between the visible and invisible cosmos is not a one-way street, but a complex dialogue where ordinary matter can reach out and reshape the dark. We find this evidence in the faintest, most dark matter-dominated galaxies we know, the dwarf spheroidals that orbit our Milky Way. In these cosmic fossils, the dark matter halo should be at its most pristine, its density smoothly increasing toward the center as predicted by the cold dark matter model. But when astronomers use the motions of individual stars to map the gravitational field within these dwarfs, they are discovering something remarkable. In many cases, the dark matter in the central regions is less concentrated than it should be. It's as if the core of the halo has been stirred up, its particles given extra energy that pushes them outward, creating a softer, flatter central density. This process is what astronomers call heating, a term that refers not to temperature, but to the random motion of particles. A heated dark matter halo is a puffed-up one, its particles moving faster and more chaotically, preventing the formation of a dense, steep cusp. The million-dollar question is, what is providing the heat? The prime suspect is the very galaxy the dark matter is meant to be hosting. This is the incredible concept of baryonic feedback, where ordinary matter fights back against its dark overlord with tremendous force. In the early, chaotic life of a dwarf galaxy, the first generations of stars were not gentle. The most massive ones lived fast and died young, exploding as supernovae. These titanic detonations did not just blow out gas and metals, they also sent powerful blast waves rippling through the galaxy's gravitational field. Imagine shaking a bowl of tiny beads. The beads represent the dark matter particles, and your shaking is the gravitational impulse from the supernova. This transfer of energy can literally push the dark matter around, redistributing it into a broader, less dense configuration. Furthermore, the gravitational potential of the galaxy itself is not static. As giant clumps of gas, massive molecular clouds form and migrate through the dwarf, their immense gravity tugs on the dark matter background, further stirring it and transferring energy in a process called gravitational heating. The dark matter halo is not an immutable sculpture. It is a dynamic entity, constantly being molded and reshaped by the violent astrophysics happening within it. But what if the heating isn't coming from within? Another fascinating possibility points to an external, invisible source, primordial black holes. If a significant portion of dark matter is made of these ancient, asteroid mass black holes, they could be the agents of this mysterious heating. As these black holes orbit within the dwarf galaxy, their immense density gives them a much stronger gravitational influence than a single particle. They would act like cosmic pinballs, transferring kinetic energy to the lighter dark matter particles through gravitational slingshot interactions, effectively heating the entire halo from the inside. Alternatively, if dark matter is self-interacting, meaning the particles can collide and scatter off one another, this would act as a form of internal friction. Over billions of years, these collisions would naturally transport heat from the outer, hotter regions of the halo toward the cooler center, causing it to expand and become less dense, perfectly mimicking the effects of baryonic heating without requiring a single supernova. This phenomenon is a critical clue in the grand puzzle of galaxy evolution. It demonstrates that the story is not simply one of dark matter providing a static gravitational well into which gas falls and forms stars. Instead, it is a tale of continuous feedback. The stars that form ultimately dictate the fate of the very dark matter halo that enabled their birth. This creates a self-regulating system. A galaxy that forms stars too vigorously will heat its dark matter halo, making it less effective at pulling in new gas, which in turn throttles future star formation. This intricate dance between light and dark is what gives galaxies their individuality and their history. The dark matter heating problem pulls back the curtain on this hidden relationship, showing us that the invisible fabric of the cosmos is not a passive stage, but an active participant in the cosmic drama, responding to and shaping the brilliant actors that play upon it. But if dwarf galaxies reveal a dynamic dialogue between dark and light, the grandest stages in the universe present an even more dramatic and revealing spectacle. This brings us to mystery number 18, the profound puzzles surrounding dark matter in galaxy clusters. These colossal cities of galaxies, each containing thousands of members swimming in a sea of superheated gas and dark matter, are not just the largest gravitationally bound structures in the cosmos. They are also immense natural laboratories where the properties of dark matter are put to the ultimate test, often with startling and paradigm-challenging results. The most famous and perhaps most compelling piece of evidence comes from a cosmic car crash of epic proportions, the Bullet Cluster. This system is actually two clusters that have recently collided, and it provides a breathtakingly clear view of the different behaviors of dark matter and normal matter. During such a violent merger, the various components react in distinct ways. The vast clouds of hot gas that fill each cluster, which comprise the majority of the normal, baryonic matter, are like two clouds of smoke colliding. Because they interact electromagnetically, they slam into each other, creating immense shock waves and slowing down dramatically. They become stuck in the middle of the collision. The galaxies themselves, being mostly empty space, sail right past each other with minimal interaction. But what of the dark matter? We cannot see it directly, but we can map its distribution by using gravitational lensing, measuring how its mass warps the light from background galaxies. The lensing maps revealed something extraordinary. The peak of the mass distribution, the dark matter, did not stay with the gas in the center. It did not even stay with the galaxies. It had raced ahead, clearly separated from both. This was a direct visual demonstration that the majority of the mass in the universe is not only dark, but it also doesn't interact with itself or with normal matter in the way that anything made of atoms does. It is truly something else, a substance that feels gravity and almost nothing else, allowing it to pass through the chaos of a galactic collision completely unscathed. The Bullet Cluster wasn't just evidence for dark matter. It was powerful evidence against a whole class of modified gravity theories that sought to explain away the need for dark matter, as those theories could not easily explain why the gravitational field would become separated from the visible matter. However, the story doesn't end there. As astronomers have studied more and more clusters, a series of subtler, more perplexing anomalies have emerged, suggesting that the simple collisionless dark matter model might need a slight tweak. For instance, some clusters appear to have their dark matter and gas surprisingly well aligned, not separated, which is puzzling if the dark matter is completely non-interacting. Other clusters show gravitational lensing patterns that are almost too strong or too concentrated, hinting at dark matter halos that are denser than simulations predict. Then there are the strange dynamics of certain mergers, where the dark matter seems to lag behind the galaxies in a way that suggests a tiny, but non-zero amount of friction, something that would be impossible if dark matter were entirely collisionless. These observations are not contradictions of the dark matter paradigm, they are refinements. They are forcing physicists to put precise numbers on the possible ways dark matter might interact. The golden bullet from the Bullet Cluster tells us that the self-interaction cross-section of dark matter, the probability that two dark matter particles will bounce off each other, must be very, very small. But it might not be zero. The anomalous clusters are now being used to place incredibly tight constraints on this property. If dark matter has any self-interactions at all, they must be weaker than anything we've ever observed in the particle world. But even an infinitesimally small interaction could, over billions of years, subtly reshape halos and influence merger dynamics. Similarly, these puzzles constrain how dark matter might couple to ordinary matter. Could there be a new, incredibly weak force that mediates interactions between the dark and visible sectors? The behavior of gas and dark matter in clusters helps us rule out entire ranges of possibilities for such a force. The future of this field is incredibly bright, moving toward a multi-messenger approach to studying clusters. We are no longer just looking at visible light or X-rays from hot gas. Instruments like the James Webb Space Telescope are peering into the hearts of clusters to study their galaxy populations in unprecedented detail. The Chandra X-ray Observatory continues to map the multimillion-degree gas. Gravitational lensing is becoming more precise with observatories like Euclid and the Vera C. Rubin Observatory, which will provide exquisitely detailed mass maps for thousands of clusters. And on the horizon is the potential for neutrino astronomy, which could one day detect the faint whisper of neutrinos produced in the violent environments of merging clusters. By combining all these different views, the visible, the X-ray, the gravitational, and perhaps even the neutrino, we will create a full, three-dimensional movie of how dark matter behaves in the most extreme environments. Each major cluster merger is a unique and powerful experiment, a chance to watch dark matter in action and learn its secrets. These cosmic collisions are our best hope for moving from simply knowing that dark matter exists to finally understanding precisely what it is. For decades, the hunt for dark matter has been a story of quiet detectors and silent results, a global effort defined by what we have not found. But one experiment running deep beneath the Italian mountains has for over 20 years told a very different story, one of a clear, repeating signal that its researchers claim can only be the long-sought whisper of dark matter. This is the heart of mystery number 19, the annual modulation signal controversy, a saga that pits a single, persistent anomaly against the collective null results of the entire field, creating one of the most enduring and heated debates in modern physics. The experiment is called DAMA/Libra, a suite of highly radio-pure sodium iodide crystals housed deep within the Gran Sasso National Laboratory, shielded from cosmic rays by a mile of solid rock. Its search strategy is brilliantly simple and rooted in the very motion of our planet. As Earth orbits the Sun, our entire solar system is also moving through the Milky Way's vast spherical halo of dark matter. From our perspective, this creates a dark matter wind that we fly into. Around June, Earth's orbital motion adds to the Sun's galactic motion, meaning we are moving fastest into this wind. Around December, our orbital motion is in the opposite direction, so our speed through the halo is at its minimum. This 6% variation in our relative speed should cause the rate at which dark matter particles collide with atoms in a detector to rise and fall in a smooth, sinusoidal pattern over the course of a year, peaking around June 2nd and hitting its lowest point around December 2nd. This annual modulation is considered a hallmark signature of dark matter, something that mundane background sources from Earth-based radioactivity or cosmic rays are not expected to mimic. This is precisely what the DAMA collaboration has reported consistently for more than 2 decades across multiple upgrades of their detector. Their data shows a beautiful, statistically robust sinusoidal wave with a period of 1 year and a phase that matches the predicted June maximum. To them, this is not just a signal, it is the signal. The persistence of this pattern over so many annual cycles makes it extraordinarily difficult to dismiss as a random statistical fluke. It appears to be a real effect happening within their detector. The problem and the source of the intense controversy is that no other experiment in the world has been able to see it. Dozens of other dark matter detectors using different target materials like xenon, germanium, and argon have achieved sensitivities far beyond DAMA and have found nothing. Not a hint of a modulation, not a whisper of the signal. This has led to a decades-long standoff. The DAMA team maintains that their result is clear evidence for dark matter interaction and that the other experiments, by using different materials, are simply not sensitive to the same type of particle. They suggest that if dark matter interacts differently with sodium and iodine nuclei than it does with xenon or germanium, the null results elsewhere are not contradictory but simply irrelevant. The rest of the physics community, however, has largely pursued a different path, trying to find any conceivable alternative explanation for the Dama signal that does not involve new physics. The list of investigated systematic effects is long and meticulous. Researchers have considered seasonal variations in temperature and humidity deep underground, fluctuations in the radon gas levels in the laboratory air, and even the annual cycle of neutrons from cosmic ray muons interacting with the rock. So far, none of these explanations have proven sufficient to account for the strength and precise timing of the observed modulation. Other, more exotic possibilities have been explored, such as the modulation being caused by a stream of charged particles from the Sun, somehow making it underground, or even a subtle effect related to the way Dama analyzes its data. Yet the signal persists, defying all conventional attempts to explain it away. This impasse has necessitated a new approach to build experiments that can directly test Dama claim on its own terms. The key is to use the exact same target material, high-purity sodium iodide crystals, but with modern techniques that allow for much better background rejection and particle identification. Two major experiments are now leading this charge. The first is Cosine 100, located in South Korea's Yongyong Underground Laboratory. It uses sodium iodide crystals like Dama, but is surrounded by a liquid scintillator veto and a vast array of photomultiplier tubes designed to distinguish between a potential dark matter signal and background radioactive events with far greater precision. After several years of data, Cosine 100 has not seen a modulation signal like Dama. Their results seem to conflict directly with the dark matter interpretation, though they continue to collect data to increase their statistical certainty. The second critical effort is the SABRE experiment, which takes the replication attempt a crucial step further. It consists of twin detectors, one in the northern hemisphere at Gran Sasso and one in the southern hemisphere in an Australian mine. This is a brilliant design to rule out seasonal systematics. Any Earth-based seasonal effect, like temperature or atmospheric changes, would be opposite in the two hemispheres. When it's summer in Italy, it's winter in Australia. A true dark matter signal, however, driven by the motion of the entire Earth through the galactic halo, would be perfectly in phase in both detectors. If both SABRE detectors see the same June modulation, it would be a monumental discovery, powerfully confirming Dama. If they do not, it will strongly point toward a local, environmental cause for the infamous signal. The resolution of this decades-long puzzle is now within sight. These next-generation experiments represent a final, definitive test. They will either validate one of the most stubborn and controversial claims in modern science, forcing a complete rethink of the properties of dark matter and why other detectors missed it, or they will finally close the book on the Dama anomaly, consigning it to the history of science as a fascinating and persistent ghost in the machine. Either outcome will be a watershed moment, bringing a long-awaited answer to a mystery that has both tantalized and frustrated physicists for a generation. While we search for dark matter's subtle gravitational whispers and the elusive ping in underground detectors, some of the most compelling hints of its presence come from the universe's most violent and energetic signals. Across the high-energy sky, astronomers have found a series of tantalizing anomalies, unexplained glows of gamma radiation that just might be the funeral pyres of dark matter particles, annihilating or decaying after billions of years of silence. This brings us to mystery number 20, the perplexing and controversial gamma-ray excesses. The most famous of these puzzles emanates from the very heart of our own galaxy. For over a decade, the Fermi Gamma-Ray Space Telescope has been mapping the sky, and its data revealed a startling excess of gamma rays pouring from the galactic center. This glow is smooth, spherical, and extends thousands of light years from the core, Critically, its energy spectrum, the specific distribution of photon energies, peaks sharply around an energy of 2 to 3 gigaelectronvolts. To many particle physicists, this looks less like a random astrophysical source and more like a textbook signature. If dark matter particles are their own antimatter counterparts, then wherever the dark matter is most densely packed, they could occasionally collide and annihilate, transforming their mass directly into energy and producing a cascade of particles that ultimately decay into gamma rays of a very specific energy. The galactic center, with its immense and dense dark matter halo, is the perfect place for this to happen. The observed gamma ray excess fits beautifully with the predicted signal for a dark matter particle with a mass between 30 and 60 times that of a proton. But the universe rarely makes things so simple. The central region of the Milky Way is also a fantastically complex and crowded place, teeming with astrophysical objects that themselves produce gamma rays. The prime alternative suspects are millisecond pulsars, the incredibly dense, rapidly spinning corpses of dead stars that beam out powerful jets of radiation. Thousands of these faint, unresolved pulsars could be scattered throughout the galactic bulge, and their collective emission could perfectly mimic a smooth, spherical glow of gamma rays. Distinguishing between these two radically different explanations, a sea of dark matter annihilations or a population of unseen neutron stars is one of the great observational challenges of our time. The key is in the details. A dark matter signal would be perfectly smooth. A population of pulsars, even a very dense one, would eventually reveal itself as a collection of individual, point-like sources if we could look closely enough. As the Fermi mission continues and our analysis techniques improve, we are beginning to see hints of such point sources within the excess, though the debate is far from settled. The verdict may ultimately require a new generation of gamma-ray telescopes with significantly sharper vision to truly resolve the heart of the glow. The intrigue doesn't stop at our galaxy's core. Unexplained gamma-ray signals have popped up in other dark matter-rich environments, each with its own story. Dwarf spheroidal galaxies, those tiny, faint satellites of the Milky Way, are prized laboratories because they are thought to be almost entirely made of dark matter, with very little of the messy astrophysical background to contaminate the signal. While most dwarfs have shown no convincing sign of a gamma-ray excess, a handful have provided intriguing, though not yet definitive, hints. The case of Reticulum Roman, too, is particularly compelling, where a faint glow was detected that is difficult to explain with known astrophysics. Similarly, some massive galaxy clusters have shown unexpected levels of gamma-ray emission from their cores. While these signals are even more tentative, they point toward a potential universal phenomenon, a signature of dark matter annihilation that scales with the density of the dark matter halo, regardless of the environment. Perhaps the most elegant potential signature isn't a broad bump of energy, but a single, sharp line. Imagine detecting a gamma-ray photon with one very specific energy, a single note in the cosmic symphony. This would be the smoking gun for dark matter decay. If a dark matter particle were to decay directly into two photons, those photons would each carry away exactly half of the particle's mass energy, creating a perfectly monochromatic spectral line. For years, astronomers have hunted for this telltale spike. The most enduring candidate is a faint line observed at an energy of 3.5 kiloelectronvolts in the combined X-ray spectra of galaxy clusters and the Andromeda Galaxy. This line has no obvious atomic transition to explain it, and its appearance in multiple, unrelated systems makes an astrophysical origin difficult to understand. However, its detection has been fraught with controversy. Some observations see it, others do not. The signal is at the very limit of our current instrumental capabilities, dancing in the noise. Like the other excesses, it remains a tantalizing maybe, a ghost in the data that refuses to be either confirmed or dismissed. The path to resolving these mysteries lies in the next generation of observatories. We need telescopes that can see the gamma-ray sky with far greater angular resolution to pinpoint whether the galactic center excess is truly smooth or riddled with point sources. We need instruments with vastly improved energy resolution to hunt for the faint, sharp spectral lines that would be the undeniable signature of decay. Missions like the proposed AMIGO and E-Astrogam could provide these revolutionary capabilities. They will also look toward the cosmic dawn, searching for the gamma-ray signature of dark matter annihilation in the early universe, a diffuse background that could be etched across the entire sky. The story of the gamma-ray excesses is a testament to the patience of science. We are sifting through an ocean of data, searching for a few precious specks of gold. Whether these anomalies finally reveal the face of dark matter or teach us something new and unexpected about pulsars and stellar corpses, they are guiding us toward a deeper understanding of the high-energy universe. Just when we thought we had a handle on the cosmic timeline, the universe throws us another curveball, one that reaches back to its very infancy. This brings us to a profound challenge known as the early formation problem, a mystery that asks a deceptively simple question: how did the universe get so sophisticated so quickly? According to our standard model of cosmology, structure forms hierarchically. After the Big Bang, tiny dark matter clumps slowly merge and grow, gradually building up to form the first stars, then small galaxies, and eventually the massive galaxies we see today. This process is supposed to take billions of years, but our telescopes are now showing us that the universe didn't get the memo. We are finding massive, mature galaxies and impossibly large supermassive black holes existing at redshifts so high that we are seeing them as they were only a few 100 million years after the Big Bang. These are not cosmic infants, they are cosmic toddlers that somehow built skyscrapers while they were still learning to crawl. The James Webb Space Telescope has been at the forefront of this revelation, its powerful infrared eyes peering further back in time than ever before. It has found galaxies that are not only shockingly large but also incredibly structured, with disks and bulges that suggest a long and quiet history of mergers and growth, a history the universe simply didn't have time to provide given its age. Similarly, astronomers have found fully formed quasars, powered by black holes billions of times the mass of our Sun, shining in an era so early that there's no clear physical mechanism to explain how they could have gathered so much mass so fast. It's the equivalent of finding a fully grown ancient redwood tree in a forest that was just seeded a year ago. The standard model of cold dark matter and its gradual, bottom-up structure formation appears to be struggling to keep up with this accelerated cosmic schedule. This premature aging of the cosmos points toward one of two possibilities, both revolutionary. The first is that the initial conditions of the universe were primed for faster growth. The seeds of all structure are the quantum fluctuations imprinted during inflation, the period of exponential expansion in the first fraction of a second. Perhaps inflation itself was different than we think. Modified inflation models could have produced enhanced small-scale power, meaning the primordial density fluctuations were significantly stronger on the scales of galaxies. This would have created more pronounced dark matter overdensities right from the start, allowing gravitational collapse to begin much earlier and proceed much faster, giving those first galaxies and black holes a massive head start. The second, and perhaps more intriguing, possibility is that the properties of dark matter itself are the key to this cosmic speed run. Standard cold dark matter is cold and collisionless, meaning it moves slowly and only interacts via gravity, which leads to that slow hierarchical growth. But what if dark matter was slightly different? For instance, if dark matter has even a small ability to interact with itself, a property known as self-interacting dark matter, these interactions could allow it to dissipate energy and collapse into dense clumps much more efficiently than collisionless matter can. Alternatively, if a fraction of dark matter is made of something even more exotic, like primordial black holes that formed in the first second after the Big Bang, these black holes would have been ready-made gravitational seeds. They would have started collecting gas and merging with each other immediately, providing a huge jumpstart on the formation of both galaxies and the supermassive black holes at their centers. This would essentially be a top-down formation channel operating alongside the bottom-up one, fast-tracking the universe's development. The James Webb Space Telescope is not just creating this problem, it is also our best tool for solving it. By conducting deep, wide surveys, it is providing a statistical census of these early, massive galaxies. The number, size, and internal structure of these high redshift objects are powerful constraints. They tell theorists exactly how much extra power or what kind of exotic dark matter physics is required to make the models fit the data. Every new galaxy discovered at the edge of time is another data point, another clue in the detective story of the early universe. The early formation problem is more than a chronological puzzle. It is a direct probe into the physics of the very beginning. By understanding why the universe grew up too fast, we might finally learn what dark matter is made of, or even discover that the inflationary epoch was far more complex and fertile than we ever dreamed. But perhaps the most intimate and telling clues about dark matter's true nature come not from the grandest collisions, but from the subtle, almost imperceptible misalignments within them. This brings us to a discovery so precise it borders on the uncanny. Mystery number 22, the dark matter baryon velocity offset. Imagine watching a car crash in extreme slow motion and noticing that the invisible driver is thrown just a fraction of a second ahead of the visible car. This, in essence, is what astronomers believe they are seeing in some merging galaxy clusters. The dark matter halo and the bulk of the ordinary matter, primarily the multimillion-degree gas that fills the cluster, are not moving in perfect lockstep. There appears to be a slight lag, a tiny but measurable difference in their velocities as they separate after a collision. This observation is a direct probe into the fundamental properties of dark matter. In the standard model, dark matter is completely collisionless. During a cluster merger, the two dark matter halos should pass through each other without slowing down, emerging on the other side at their original speed. The hot gas, however, is a different story. It's made of protons and electrons that interact strongly via electromagnetic forces. When two clouds of this gas collide, they behave like two clouds of smoke, creating immense shock waves and drag forces that slow them down dramatically. This is the effect that created the stunning separation in the bullet cluster. But in a handful of systems like the famous musket ball cluster and Abel 520, the data suggests something even stranger. The dark matter doesn't just race ahead, it seems to have a slightly different velocity vector than the gas. It's not just leading the charge, it's moving on a subtly different path. This could be the first hint that dark matter isn't entirely aloof. It might experience a tiny but non-zero amount of drag or interaction with the sea of ordinary particles it's moving through. The implications of such a discovery would be revolutionary, pointing directly to a new force in nature. If dark matter particles can bump into protons, even incredibly rarely, it would mean they interact through something more than just gravity. This could be mediated by a new, as yet unknown fundamental particle, a dark photon or some other portal that allows the dark sector to talk to our visible world. The magnitude of the observed velocity offset would allow physicists to calculate the exact strength of this interaction, placing a precise number on a property we currently assume is zero. It would open up an entirely new field of dark sector physics, moving us from simply mapping dark matter's gravity to understanding its dynamics and relationships. Yet, in a field as complex as cosmology, extraordinary claims require the most rigorous scrutiny. The primary alternative explanation is that we are not seeing new physics, but are instead being fooled by the incredibly complex astrophysics of these chaotic environments. The aftermath of a cluster collision is a messy place filled with turbulence, shock fronts, and sloshing gas. It is possible that complex hydrodynamical effects, like the mixing of different gas phases or the presence of unseen substructure, could create a false signal in our data. The dark matter map is not a direct photograph. It is inferred through the subtle warping of light from background galaxies, a technique called weak gravitational lensing. If our model of the mass distribution is even slightly imperfect, if we misjudge the geometry of the collision or the presence of other, smaller structures along our line of sight, it could introduce a spurious offset that looks exactly like a velocity lag. The key is to move from a handful of puzzling cases to a large statistical sample. Only by observing many such collisions can we distinguish a true, consistent signal from random noise or astrophysical mimicry. This is where the future of astronomy promises to bring clarity. The solution lies in multi-messenger observations, using every tool at our disposal to build a complete three-dimensional movie of these cosmic crashes. The Chandra X-ray Observatory provides an exquisitely detailed map of the hot gas. The Hubble Space Telescope and its successor, the James Webb Space Telescope, offer the high-resolution imaging needed for precise weak lensing mass maps. And observatories like ALMA can track the motion of cold gas within the system, providing an independent velocity measurement. By combining these views, we can cross-check our results and build a robust, self-consistent model of the entire event. The upcoming Vera C. Rubin Observatory and the Euclid Space Telescope will take this to a new level, discovering and analyzing thousands of merging clusters, providing the vast dataset needed to see if this velocity offset is a rare fluke or a universal feature of dark matter's behavior. Each collision is a unique and powerful natural experiment, and by watching enough of them unfold, we will learn whether the universe's dominant matter is a ghost that passes through walls without a trace, or a shadow that occasionally, subtly brushes against our own. Just when we think we understand the rules of the cosmic game, the universe delivers a paradox so profound it seems to break them entirely. For decades, the foundational story has been clear. Galaxies are born within and defined by their massive halos of dark matter. This invisible scaffolding dictates their growth, their shape, and their very existence. Nowhere was this truth thought to be more absolute than in the faint, diffuse dwarf galaxies that orbit larger hosts like our Milky Way. These tiny systems, with their feeble gravity, should be utterly dominated by their dark matter, held together by its overwhelming presence. This is why the discovery of galaxies like NGC 1052 DF2 and DF4 sent such a seismic shock through the world of astronomy. These aren't just outliers, they appear to be revolutionary exceptions. Initial studies suggested they contain staggeringly little, if any, dark matter at all. It's the equivalent of finding a ship sailing across the ocean with no hull, just a sail. A seemingly impossible object that defies our most basic understanding of how the universe works. The story of these galaxies begins with precise measurements of their internal motions. In a normal dwarf galaxy, stars zip around at surprisingly high speeds, a clear indicator that they are being whipped along by the powerful gravity of an unseen dark matter halo. But when researchers pointed the Dragonfly telephoto array and later the Hubble Space Telescope at NGC 1052 DF2, they measured the velocities of its star clusters and found them to be languid and slow. The stars were moving just fast enough to account for the gravity of the visible matter. They could see the stars and a tiny bit of gas. There was no room left for dark matter in the ledger. The calculated total mass was almost exactly equal to the mass of the stars themselves. For a galaxy, this is bizarre. It's like weighing a person and finding that their weight is identical to the weight of their clothes with no body inside. The subsequent discovery of a second such galaxy, DF4, in the same region of sky, confirmed that this wasn't a one-off fluke or an observational error. It suggested a new class of object, dark matter-free galaxies. This finding immediately ignited a fiery debate within the astronomical community. a debate that hinges on the painstakingly difficult task of cosmic accounting. The entire argument rests on two critical and challenging measurements: distance and mass. The distance to these galaxies is paramount. If they are farther away than we think, they must be physically larger and brighter to appear as they do. A larger, brighter galaxy would naturally need more mass to keep its star clusters gravitationally bound, which could mean the missing dark matter was there all along. We just underestimated the scale of the system. Some teams using different measurement techniques have indeed argued for a greater distance, which would partially resolve the anomaly. The other pillar is the mass estimate itself, derived from the observed velocities of the star clusters. If those 10 or so clusters are not truly bound to the galaxy but are instead slowly drifting away, their slow speeds would be an illusion, not proof of a lack of mass. Untangling this requires exquisitely precise data, and even the smallest uncertainty can tip the scales of the argument. So, if these galaxies truly are as close and as massive as the original measurements suggest, how could they possibly have formed without dark matter? This question forces astrophysicists to consider a dramatic and violent origin story: that these galaxies are not primordial objects at all, but celestial orphans born from catastrophe. The leading theory is that they are tidal dwarf galaxies. Imagine two large, gas-rich galaxies colliding in a slow-motion gravitational dance. During this immense collision, tidal forces can pull vast streams of gas and stars out of the parent galaxies, flinging them into intergalactic space. This ejected material, now free from the overwhelming gravitational pull of its original dark matter halos, can collapse under its own gravity to form a new, second-generation galaxy. This new galaxy would be born from pure baryonic matter, the stars and gas we can see with little to no dark matter in its composition. This would explain the impossible: a galaxy that formed not from the top-down collapse of a dark matter halo, but from the bottom-up assembly of ordinary matter alone. The fact that DF2 and DF4 are found near a large elliptical galaxy, NGC 1052, provides a plausible site for such a dramatic galactic event in the relatively recent past. The implications of this discovery stretch far beyond these two peculiar galaxies. If confirmed, their existence is a double-edged sword. On one hand, it would be a stunning validation of the tidal dwarf galaxy formation process, a phenomenon that has been theorized for decades but never so clearly demonstrated. On the other hand, it would also validate the very existence of dark matter itself. The reason is beautifully logical. You can only have a galaxy without dark matter if dark matter is a real, tangible thing that can be separated from normal matter. If alternative theories of gravity like MUND were correct, you cannot have a galaxy that lacks dark matter because the modified gravity effect is tied to the visible mass. There would be no way to separate the two. Therefore, the very existence of a dark matter-free galaxy is perhaps the most ironic and powerful evidence that dark matter is in fact a particle. It proves that dark matter is not an immutable property of gravity, but a distinct substance that can be physically stripped away. The final verdict on this cosmic mystery now rests with the next generation of astronomical observatories. The James Webb Space Telescope, with its unparalleled infrared sensitivity and resolution, is perfectly suited to make the definitive measurements. It can study the individual stars within these galaxies to get a more precise distance estimate, and it can scrutinize the motions of star clusters with far greater accuracy than ever before. Simultaneously, the Vera C. Rubin Observatory will soon begin its monumental survey of the sky, likely discovering dozens more of these enigmatic objects if they exist. A larger sample size will allow astronomers to study their properties statistically, where they are found, what they look like, and how they relate to their environment. This will help determine if they are all formed through tidal interactions or if there are multiple pathways to creating a galaxy without its dark shadow. The mystery of these seemingly impossible galaxies forces us to refine our theories and sharpen our observations, reminding us that the universe is always more inventive and surprising than we can possibly imagine. But if the grand collisions of galaxy clusters show us dark matter on its largest scales, perhaps its most fundamental secrets are hidden in the very smallest clumps it can form. This brings us to a prediction so profound it challenges the limits of our observation: the mystery of the dark matter microhalos. Our most advanced cosmological simulations don't just forecast the giant halos that host galaxies. They trace the process of hierarchical structure formation all the way down to the very bottom. They predict that the universe should be teeming with an astronomical number of pristine, Earth-mass dark matter clumps that formed in the universe's breathtakingly early moments and have survived virtually unchanged for over 13 billion years. These microhalos are not mere theoretical curiosities. They are direct relics of the primordial universe. Their story begins with the infinitesimal quantum fluctuations imprinted during the inflationary epoch, a period of exponential expansion in the very first fraction of a second after the Big Bang. These random wrinkles in the fabric of spacetime were then stretched to macroscopic scales, creating a spectrum of overdensities. After the universe cooled and neutral atoms formed, gravity began its patient work. The smallest and densest of these fluctuations were the first to collapse, their growth ceasing once the universe expanded enough to dilute their material. This process, known as free streaming, sets a minimum mass for the first dark matter structures. For the most popular cold dark matter models, this minimum mass is astonishingly small, somewhere between the mass of the Earth and that of a large asteroid. Countless trillions of these microhalos are predicted to have formed, and because dark matter is collisionless, they would not evaporate or dissipate. They should persist today as invisible, ultra-dense nuggets swarming like a cosmic fog through the halo of every galaxy, including our own Milky Way. We are, according to the theory, living in a sea of these ancient fossils. The problem and the heart of this mystery is that we haven't found them. If they are as numerous and as dense as the simulations suggest, their collective gravity should leave a detectable imprint on the universe around us, yet this evidence remains elusive. This absence forces astronomers to become detectives of the invisible, devising incredibly clever methods to hunt for the subtle gravitational tremors these microhalos would cause. One of the most promising techniques is called femtolensing. When a distant gamma ray burst, the most powerful explosion in the universe flares brightly. Its light travels across billions of light years to reach us. If a dense, compact object like a microhalo drifts through the path of this light, its gravity would act as a lens, creating interference patterns that would leave a specific, oscillating signature in the gamma ray spectrum. While searches for this signal have so far come up empty, they have placed the first meaningful constraints on how many such objects could exist. Another method listens for the whispers of these halos in the precise rhythms of the cosmos. Pulsars are the universe's most accurate clocks, spinning neutron stars that beam radio waves at intervals so regular they rival atomic clocks. A microhalo passing near the line of sight between a pulsar and Earth would slightly perturb the spacetime along that path, causing a tiny, temporary delay in the arrival time of the pulses. Global networks of radio telescopes, known as pulsar timing arrays, are now sensitive enough to detect the gravitational wave background from merging supermassive black holes. They are also on the cusp of being able to detect or rule out the presence of a population of wandering microhalos. Perhaps the most elegant probe involves the stellar streams we discussed earlier, those beautiful ribbons of stars torn from dwarf galaxies. The gravitational pull of a single, wandering microhalo would be enough to create a visible kink or gap in one of these streams. By meticulously mapping these structures with observatories like Gaia, astronomers are turning the Milky Way's halo into a gigantic dark matter detector, scanning for the telltale scars left by these invisible intruders. The fact that we see many smooth, undisturbed streams suggests that the microhalo population might be far sparser than expected. So, where are they? The continued absence of these predicted microhalos points toward one of two revolutionary conclusions. The first possibility is that dark matter is not as cold and simple as we thought. If dark matter particles had even a tiny amount of thermal motion in the early universe, a property known as warmth, this would suppress the formation of the very smallest structures. Warm dark matter would free stream out of the smallest overdensities, erasing them before they could collapse, effectively putting a lower limit on the mass of the first halos. The lack of microhalos would therefore be a powerful indicator that we need to shift our search toward lighter, faster-moving dark matter candidates. The second, more dramatic possibility is that dark matter is not a sea of individual particles, but a collective field. Theories like fuzzy dark matter propose that dark matter could be made of ultra-light particles, so light that they behave more like a wave than a discrete particle. On large scales, this wave would act just like cold dark matter, forming the cosmic web we observe. But on small scales, its wave-like nature would create a natural pressure that prevents it from collapsing into ultra-dense microhalos. The absence of these small clumps wouldn't be a problem, it would be a direct prediction of the theory. The hunt for dark matter microhalos is a quest to understand the universe at its absolute smallest scales of structure. Finding them would confirm our deepest theories about cosmic evolution and the cold, collisionless nature of dark matter. Their continued absence, however, is not a failure but a guide, pushing us toward a richer and more complex understanding of the universe's dominant ingredient. It is a reminder that sometimes the most profound truths are hidden not in the grand and the obvious, but in the quiet absence of the small and the expected. And so we arrive at the ultimate question, the grand synthesis that lies at the heart of all these cosmic puzzles. After journeying through 24 profound mysteries, from the spinning of galaxies to the voids in space and the whispers in underground labs, we are finally forced to confront the fundamental enigma. What, in its essence, is dark matter? We have mapped its gravitational shadow across the entire universe, yet its true face remains hidden. The answer is not a single entity but a spectrum of breathtaking possibilities, each with the power to rewrite physics and reshape our cosmic story. For decades, the leading contender was the WIMP, the weakly interacting massive particle. This hypothesis was beautiful in its simplicity and its connection to other frontiers of physics, particularly supersymmetry. A heavy, stable particle left over from the Big Bang, interacting only through gravity and the weak force, explained so much with such elegance. Yet, as we've seen, the relentless silence from deep underground detectors has pushed the WIMP into a corner, forcing us to broaden our gaze. The action represents a completely different vision. Instead of a heavy particle, it is unimaginably light, a billionth of a billionth the mass of an electron. It would behave less like a discrete bullet and more like a pervasive, oscillating energy field permeating all of space. Its detection requires not massive vats of xenon, but incredibly powerful magnetic fields designed to convert these ghostly waves into faint photons. Then there are the primordial black holes, a concept that ties dark matter directly to the universe's violent birth. These would not be black holes formed from dead stars, but ones forged in the searing density of the first second after the Big Bang, ranging in size from a mere asteroid to a giant planet. They are a compelling idea, though searches for their telltale gravitational lensing effects have so far limited how abundant they could be. The list grows even more exotic. Sterile neutrinos are hypothetical heavier cousins to the standard neutrinos we know, particles that would interact only through gravity, making them perfectly dark. Some models even suggest dark matter could be a composite object, not an elementary particle at all, a kind of dark atom made of dark protons and dark electrons interacting through a dark force we cannot feel. This idea of a rich, dark sector with its own complexity and physics is perhaps the most intriguing of all. It could explain why dark matter seems to have a mind of its own, forming unexpected structures like planes of satellites or exhibiting a diverse range of densities that don't always correlate with the visible matter. Perhaps the dark universe is as rich and varied as the visible one, with its own dynamics and interactions happening just beyond our perception. Each candidate offers a different key to unlocking the mysteries we've explored. A self-interacting dark matter particle could solve the core cusp problem by allowing dark matter to smooth itself out, and it could stabilize the planes of satellites through subtle friction. A warm dark matter particle with its slight intrinsic motion would suppress the formation of the smallest microhalos, explaining why we don't see their gravitational effects. An axion or a sterile neutrino could account for the anomalous gamma-ray signals from galactic centers, and the concept of a dynamic dark sector with multiple components and forces could be the unifying theory that explains why dark matter behaves one way in galaxy clusters and another in dwarf galaxies, appearing absent in some objects and overwhelmingly dominant in others. This brings us to a profound realization: dark matter may not be one thing. The universe has never been simple. Why should its dominant form of matter be any different? It is entirely possible that the dark sector is a mixture, a cosmic cocktail of WIMP, axions, and primordial black holes, each contributing to the whole in different ways and in different environments. This would certainly complicate the story, but it would also match the beautiful complexity we see everywhere else in nature. The path to discovery now lies in a multi-pronged assault. We will continue to listen for the faint ping in deeper, more sensitive underground labs. We will build larger magnetic arrays to hunt for axions. We will use telescopes like JWST, Rubin, and Euclid to map the cosmic web in ever greater detail, searching for the subtle gravitational fingerprints of different dark matter behaviors. And we will watch the skies for the explosive signals of annihilation or decay. The true nature of dark matter is the final piece of a puzzle 13.8 billion years in the making. Its discovery will not just fill a blank space in our textbook, it will open a door to a universe twice as large and complex as we ever imagined, revealing that we have been living in the light of a far vaster and more mysterious darkness. And so our journey through the cosmos's greatest enigma brings us to a final, breathtaking vista. We have navigated 25 profound mysteries, from the silent, gravitational pull that spins galaxies too fast to the hauntingly empty voids between the cosmic web. We have wrestled with the too-big-to-fail problem, pondered the perplexing planes of satellites, and felt the tension in the Hubble constant. We have listened for the whispers of WIMP in deep underground labs, searched for the gamma-ray glow of annihilation, and been captivated by the impossible galaxies that seem to lack dark matter entirely. Each puzzle, from the lithium deficit in ancient stars to the potential dark disk right here in our own galaxy, is a single thread in a vast and intricate tapestry of ignorance. Yet together they form a coherent picture of a universe where the stuff we understand, the atoms that make up our world and our bodies, is nothing more than a delicate shimmer on the surface of a deep, dark ocean. These are not isolated problems to be solved one by one with minor tweaks to our equations. Collectively, they are the unmistakable signature of new physics, a fundamental shift waiting to happen. They point toward a reality where the dark sector is not a single, simple particle but a rich and complex universe unto itself, operating by rules we have yet to imagine. The core cusp problem and the diversity of rotation curves suggest a dynamic dialogue between dark and light matter. The persistence of satellite planes and the potential for self-interaction hint that dark matter might not be entirely aloof. The early formation of massive galaxies seen by James Webb and the puzzling velocity offsets in cluster collisions all scream that our standard model of cosmology, for all its success, is an incomplete chapter in a much longer story. But we are not left in the dark. We are standing on the brink of a new era of discovery, armed with tools of unimaginable power. Deep underground, next-generation experiments like LZ and Enigmas are achieving sensitivities that will finally probe the most promising corners of the WIMP parameter space, while dedicated action hunters like ADMS are listening for the faint hum of an ultra-light field. In space, a new generation of observatories is turning its gaze to the cosmos. The Vera C. Rubin Observatory will begin its legacy survey of space and time, mapping billions of galaxies and using weak lensing to weigh the dark universe in a way never before possible, directly testing the cold dark matter paradigm on large scales. The Nancy Grace Roman Space Telescope will peer into the hearts of galaxies to study their formation. And of course, the James Webb Space Telescope is already revolutionizing our view, looking back to the very first galaxies to understand how dark matter shaped them and searching for those dark matter-free dwarfs to confirm their impossible existence. The Euclid Space Telescope is meticulously mapping the geometry of the dark universe, and future gravitational wave observatories will listen for the echoes of primordial black holes. This is not a passive waiting game. It is an active, thrilling hunt, and every one of us is living through it. The next decade will be remembered as the time we began to see the unseen. So the next time you look up at the night sky, remember that the stars and galaxies are just the visible embroidery on a canvas of profound darkness. That darkness is not empty, it is the main event. It is the source of most of reality's substance, the architect of the cosmic web, and the holder of the universe's deepest secrets. Let the mystery not discourage you, but ignite a profound curiosity. For in the darkness, we are not just searching for particles, we are searching for our place in a cosmos far grander and more mysterious than